doesn't seem to, this doesn't seem to work. What?
Yeah, no, you have to, there is a trick, which is basically
Okay.
you have to go back to the presentation, otherwise, try now. Because when we switch on Zoom, yeah,
It's fine. I just need to know if this works or not.
yeah, she's trying, to move forward in the presentation.
No, I'm trying to move backwards.
Oh, backwards.
Or forward.
But she's trying to control
Let's
the.
call it a fail. I don't have enough
Oh, hold it.
expertise.
Is this not on?
Oh,
this
maybe
is
it's not on. Oh, green light.
That was
Good.
it.
Yes.
Oh, yeah, that's
All
working.
right,
Works.
good.
Let me see if there is somebody.
Okay.
Hello, can I ask everybody to start? Okay, so thank you for coming to the last day and for showing up after the Mystery Day. We hope you had fun last night. So today we are going to switch gear in talk at the beginning about Sophia. So Margaret is going to talk about Sophia. Margaret Meisner, who is the director of Sophia, is going to talk about Sophia opportunities for astro training.
Okay, thank you, Roberta. Can everyone hear me? Is the mic actually working? Okay, excellent. Okay, so Sophia and Astro 2020, we all know what the decadal said, but the truth is that Sophia is the far infrared observatory for this decade, and it is the only far infrared observatory in the world that we can make these measurements at. So let's use Sophia while we still have it to pursue the Astro 2020 agenda, both scientifically and technologically. Sophia has transformed over the past 2 years with tremendous growth in science productivity. And this link that's on this slide, you can also find on Sophia website, points to this report, Status and Future Prospects, which captures this transformation and the future growth that I'll cover just only a little bit here, but it's a very thorough report about Sophia science, operations, and opportunities. Now, Sophia advances Astro 2020 science by directly addressing 1/2 of the decadal science priorities in all 3 science themes. And this is good news for our field, because our field is important to actually addressing Astro 2020 science. The 3 science themes: cosmic ecosystems, worlds and sun in context, new messengers and new physics. And so join the Sophia community, which is 2,138 strong and growing. To exploit the opportunity Sophia provides to train the next generation of astronomers and instrument builders who will define, develop, and use the future far infrared observatories outlined in the Astro 2020 report. Now, these next 3 charts are a bit of an eye chart, but it is the traceability matrix of Sophia science and capabilities to the decadal science questions. This can also be useful if you're thinking of future probes or further in the future. So it's a very nice template. You can find it in the report. What this will show is on the left is the decadal science question. The middle one is the key measurement you need to address this question. The third column on the right is the Sophia instrument that you need to make those measurements. And on the right are actual observations that have been or we are doing right now that addresses these decadal questions. So I'm just going to take one as an example. This is cosmic ecosystems theme, and this is equivalent to the NASA key question, how did we get here? So the first one is, how do star-forming structures arise from and interact with the diffuse interstellar medium? Sophia covers, and the far infrared wavelength covers, these key cooling lines, the C2 line, 158 micron, and both oxygen lines. We also cover light hydrides, which are uniquely accessible in this wavelength. And Sophia's high spectral resolution, you can get kinematics. And we have far infrared polarization, which tells you a lot about the structure of the interstellar medium. We have 3 instruments, GREAT, PFLS, and HAWK Plus, and we have an instrument roadmap that has potential for terahertz mapper. We have a lot of the ones that are highlighted in purple are key legacy programs, large data sets that we're providing, that these teams are providing to the community. Feedback, High Gal, LNC Plus, GalMag, and C Plus Squad are all key programs in this area. As you can see, we do a lot of work in the cosmic ecosystems area. Are we alone, or worlds and suns in context? This is an area in which we're growing. We do a lot of work in the solar system. A lot of the work Sophia does is sort of templates or things you can calibrate for more distant objects. In the case of trying to understand how life evolved, so let's just take this one. How do habitable environments arise from and evolve in the context of their planetary systems? Well, these are the measurements we can make. Water, oxygen 1 phosphine, the D to H ratio, using forecast axes in gray. We have one legacy program that I'm calling Lunar, and it's to map. It's a follow-up on that detection of water on the sunlit surface of the moon. And it's to map water on the surface of the moon and see how that water content varies, which will inform how we think about how water gets transported. And we all know that water is essential for life as we know it. And this last one is certainly an area of growth. How does the universe work? New messengers, new physics. And this key decadal question, transforming our view of the universe by combining information from light with these other things, is important. And we've been talking about in this forum the importance of pursuing time domain astronomy. And this is an area, I would say, of growth for this field, because our missions have been very short-lived. We have 3 years to work in the far infrared, and we're seeing the universe for the first time. So we're just trying to map things and see them for the first time. Time domain is like you're repeating the same thing. And so this is an area, for example, that you can explore quite well with Sophia. We have a multi-cycle monitoring program to try to explore what are the types of things you can realize, what's the new type of information you can get. And of course, supernovae is sort of a key area here. All right, so Sophia science. So Sophia's efficiency and science productivity are on the right trajectory for Sophia to achieve its full scientific potential. Our annual publications rate have doubled over the past 3 years, and they'll double again in the next 2. And these are topics ranging from measuring the Earth's atmosphere to high Z galaxies. This link takes you to this brochure, and there's also brochures by Lars and Jessica's posters of the Sophia Science remarkable results. There's some of our highlights that literally have come out in the last 2 years. We've had this outpouring of science. Now, legacy science programs are 30% of the Sophia schedule now. I'm just going to highlight just 3 of them, just to give you what is capable. On the right, we have a picture of the pillars of creation in Hubble. And then it transforms into the C+ map, where you have the kinematics that show how the ISM got this beautiful structure that Hubble images. This directly addresses how do star-forming structures arise from and interact with the diffuse interstellar medium. Its key line is looking at high spectral resolution observations for the C+ line, where you can measure not only this main cooling line to measure the PDRs, but you get that kinematic mechanical information to understand what the main feedback is. And the key thing they are finding is that it's stellar winds that is doing most of the feedback, most of the energy feedback in these regions pretty consistently. On the right again is the Eagle Nebula, and this is just about complete. We're going to complete it this summer. We have GalMag, which is measuring the magnetic fields of galaxies. And this is led by Enrique Lopez Rodriguez at Stanford. It uses HAWK+. HAWK+ really has inserted the missing information on magnetic fields. And it's really transforming how we think and understand about the interstellar medium and its processes. 2 decadal questions: how do metals arise from through in and out of galaxies, and how do star-forming structures arise from interact with the diffuse interstellar medium? Turns out the magnetic fields are key in funneling and shaping and controlling the star formation process. On the left is M82, and it shows these magnetic field lines actually guiding the galactic wind out into the intergalactic medium. In the middle, you have the merging galaxy, Centaurus A. And this merging galaxy, what they find is that there's an amplification of the magnetic field. It's showing like how do magnetic fields grow over time. They're finding that this chaos of collisions has actually helped. And on the right, you have the iconic M51 galaxy showing the magnetic field structures, both in the spiral structure, but also again, this turbulence from the feedback actually amplifies that magnetic field. And the last one I'll just highlight, again, we have 9 total legacy programs going on, is Lunar. And this is mapping using the forecast GRISM. They're mapping this water on the surface of the moon in the sunlit regions and throughout, and seeing how temperature and diurnal cycle affects it. Now, SOFIA has science opportunities. Our cycle 10 proposals have been reviewed scientifically, and we're doing a planning process to see which ones can be scheduled. We will have an archival funding call. May 2022 will probably be the latest. Possibly it'll come out the end of April. The deadline will be in the summer, no later than July. So stay tuned for that. This is a great opportunity. The SOFIA archive, which is hosted by IRSA, has a very rich amount of data over all these things, all the observations. There are a lot of beautiful data sets that are currently unpublished. All right, now, just to give a little context of how do we value SOFIA in terms of a science observatory. And so the slide is SOFIA versus space missions. What I show here in this plot is number of papers per year versus calendar year. Our operation started in 2014. And what I'm showing here in red are what our cumulative publications are. And the FMR expectation is what the FMR, we had a very thorough flagship mission review a few years ago. And they said, you really need to be getting 100 publications per year. You need to reorient yourself. And we have. And because there are time delays in these intentional programmatic effects we've done, we will get there in 2 years' time. Now, SOFIA science publications, which are now at 316, are significantly higher than science return that you get from foreign for balloons. This doesn't mean that the balloon program's bad or anything like that. It just means that it's a different type of contribution. So SOFIA is an observatory, and it provides science, a very diverse science portfolio. Now, SOFIA has been compared to Hubble, which is a mature robotic. It's been there for 30 years and with a substantial archive. A better comparison is with Herschel. So that's a recent far-infrared mission that provided 23,500 hours and produced, it should say, 2,000. I have that wrong there. It has like 2,000 publications within 8 years of the launch. SOFIA has only 3,458 hours, and it's produced 316 science publication with 8 years since science operations. So if you look at the paper writing efficiency, it's about the same as Herschel. It's about 11 hours per paper. In the future, as I mentioned, we have an increase in hours coming. And so over its potential lifetime, and just, mechanically, funding aside, mechanically, it could last for the decade until we get a far infrared probe. And so science is on the uptick with SOFIA. I want to talk a little bit about the technical aspects, because when you are thinking about your probes, you need to do something that's different than what SOFIA can do. I think that's important. Otherwise, build an instrument for SOFIA at a fraction of the cost. So this shows you the SOFIA flies above 99.99% of atmospheric water. And that on the below down here, sorry for this, this image. ALMA is shown here in gray, and SOFIA shows here in blue. And so you get a lot of transparency, and that actually enables you to see these lines of C2O1, these key cooling lines, and the SED. And remember, we are the only far infrared observatory that can do this. Now, SOFIA telescope, it has a 2.5 meter effective diameter. It's reflective, visible to sub-millimeter. It's nimble, and it's excellent for mapping. It has chopping secondary optical guide camera. The temperature is 247. So I think Matt Bradford talked about yesterday about this huge win you get by going to space and chilling your telescope down. That is the big advantage over something like SOFIA. We have 5 science instruments plus the guide camera, Forecast, XES, Hawk Plus, FIFI-LS, and GREAT. And this is how we are complementary to the capabilities of currently with James Webb and ALMA. So spectral resolving power is a huge strength of SOFIA. We can accommodate large instruments that can do the high spectral resolution. And what we have here is showing you this is where forecast with forecast prisms is. That's comparable to the resolutions that you get with James Webb. XEs, you get 2 orders of magnitude higher. So you will see lines with XEs that will be blended with James Webb. Here you have GREAT, which has comparable spectral resolution to ALMA, but of course, very complementary wavelengths. And what we put in here is are these potential future far infrared instruments such as a direct detection spectrometer and a terahertz mapper. Just on continuum sensitivity, we are very complementary to James Webb. In the gray here is what JVST gets unsaturated. So James Webb starts here and goes, of course, very sensitive. That's the key thing about James Webb. Forecast will catch a lot of the bright stuff. So it's very complementary in capability. And of course, we don't currently have anything in the far infrared except Hawk Plus for imaging. Spectroscopic capability, again, this is a strength of SOFIA. This is JVST unsaturated. Here's XEs. Again, the main thing is the spectral resolving power of XEs, 50,000. So you'll see things that James Webb can't in terms of resolved power. This is where FIFI-LS is located. This is GREAT, the heterodyne instrument in terms of spectral line sensitivity. And these are what the expectations are for something like a direct detection spectrometer or terahertz mapper. The key thing about heterodyne spectroscopy is it really cares about aperture, not the temperature of the telescope. So when it comes to SOFIA and the GREAT instrument or future heterodyne instrument, it is almost comparable to space when you get to the best conditions. SOFIA is an important suborbital mission. Now, suborbitals such as SOFIA are essential to furthering science and technology to be used in these future ASTRO 2020 space missions. The balloon program, which is also a very incredibly valuable suborbital portfolio, focuses on PI-driven far infrared observations. So the far infrared technology developed in the balloon platforms can be applied in a more capable, complex instrument on SOFIA, which has a larger aperture, power, mass, and volumes. Now, ASTRO 2020 requests a technology development plan SOFIA could play a role in this. SOFIA offers the only reliable and repeatable suborbital platform. The astronautical community's proposals directly address or drive the program, and instruments can be replaced or updated with new ones. Now, we do have an instrument roadmap that starts off with a Hawk Plus instrument upgrade, 2 new instruments, and then if you look far in the future, potentially another one. But just talking about step 1, so is replacing the Hawk Plus detectors. This will increase the mapping speed of magnetic fields by up to a factor of 4. It's in a formulation phase where there's been funded for the TES development or NIST for MKIDS for the detector replacement, and we're expecting those proposals by late spring or summer. And these are proposals to do the upgrade that will be evaluated. The direct detection spectrometer, the key science case is 30 to 120 microns, measuring the HD mass, HD as proxy for H2. SOFIA will be able to get some of the brighter ones. The probe concepts, of course, will get a very complete sample. Here you're pushing the sensitivity by a factor of 10 with SOFIA. And with the terahertz mapper, you're basically filling the focal plane of SOFIA with heterodyne receivers, and that increases the mapping speed by 13. So you could literally sort of do the feedback survey sort of on a snapshot mode. And so just to summarize, SOFIA addresses 1/2 of the decadal science priorities. ASTRO 2020 outlines the need for a technology maturation plan for great observatories, and Sophia could play a role in this. One of the great observatories is this far infrared observatory, like the Origin Space Telescope concept. I point you again to the link for our report on its status and future prospects. And my key message to you is the far infrared probes need to do what Sophia cannot do. Otherwise, for tiny fraction of the cost of a probe, just build an instrument for Sophia. And my question to you is, how can we use Sophia to achieve ASTRO 2020? I hope we can have a discussion about that. And on the fun side, I think flying Sophia should be on every astronomer's bucket list. I did that for the first time 3 weeks ago. It was awesome. And we are hiring postdocs. Thank you.
Margaret, questions for Margaret? Okay.
Margaret, we didn't have a chance to delve into this in our chat outside, but how are you planning to move forward on the new instrument development in light of the budgetary landscape?
Right. No, it's a very good question. It's a programmatic question. I have talked to the project and they said that they are pushing ahead to get these formulation proposals. This summer, they want to see what those are, and they'll be playing it by ear about how to move forward on something like that. But certainly, the science is valuable, and I think since these detectors will be new, it's at least helping push along some of the technology development for detectors.
NASA guidance is that you will have a science maturation program for the flagship missions in the next few years. So maybe concerning the flagship missions, we need to first work out the science that's compelling. Obviously, Sophia can play a big role in supporting that. Have you started to work out how that might look in terms of a formal traceability matrix or so?
Well, I think that science traceability matrix that's in this report link shows how what the science Sophia is doing maps to the ASTRO 2020 decadal science reports, and we do directly address one half, and it's because Sophia's program is so broad. It covers a lot of astrophysics, and I think, the reason I took this job is because I thought it was important to have access to this wavelength range until at least we have a probe in space and within reach, because I think it's important both for training, but also exploring what is the science that you can do to keep that active and engaged.
Great. Thank you very much for that overview. I want to ask about the current year-to-year existence of Sophia, and I see that as the biggest drawback. If you want to do some instrument development, you should have a mission.
Yes.
2 years at the minimum, right?
Yes.
How do we get to the point where that can be possible? It's been year to year for a long time. How do we overcome that? And that's a key thing to do.
No, I agree that is a challenge of trying to do an instrumentation program if you don't know if when you finish it, it's going to be flying. It is a chicken and egg problem. It's something I have discussions with the project on. I don't have an answer beyond that. I think there are some compelling science cases with the workshop for pursuing those instruments and achieving more, but again, what you're asking is a programmatic question. That's, I'll take that back to the project.
First of all, Margaret, I'd just like to, congratulate you. The turnaround in the last 2 years. It's a big thing, and you should work on it.
Well, thank you.
Thank you. The second thing is it's not really about Sophia. Is Dominic still here? Okay, maybe I'll fill in for him. the notion of what the program that ESTIG 2020 recommended, the name of the program has key words in it. It's the Mission and Technology Maturation Program. It's not the Science Maturation Program.
Okay.
And the first part of that program, as NASA is getting it set up, and I don't mean to speak for NASA, but Dominic isn't here. I'll fill in a little bit. Is and there's a workshop coming up on what's called precursor science. The definition of precursor science is NASA has written it down, perhaps with an unfortunate name, but the definition is science that will affect the design of the mission. Science that will do science that is valuable, science that would be then realized fully isn't what that program is at. Science that affects the design of the mission. So we can talk about that later, but it's an important distinction, especially thinking about what's going into that program, what NASA will be doing. Now, the ASTIG 2020 recommendation for that program is a lot of money. It's $1.2 billion. The first $800 million of it going to flagship number 1. Flagship, and $400 million into flagship 2 and 3, and read the next grade. Flagship, so there's a lot of money there. Mission and technology integration.
Okay, no, that's a good point. And this workshop he mentions is basically in a month. It's like the end of April or something. And it would be useful if people from this community participated in that.
John's on the organizing committee.
Okay.
Yeah, so I'm happy to talk about it.
Yeah. It's supposed to cover all missions. I mean, or, you know, all great observatories, not just the next one. So it would be important to get our voice heard there.
That is important.
Last question.
Yeah, I mean, I think this follows along those lines, but I guess I sort of wanted to emphasize the importance of Sophia science for being able to have sort of the science developed for the probes. You know, for example, the areas that I was working on and discussing for the far infrared light emission, we really don't understand it very well and where it comes from. And without Sophia as sort of the background, by the time we have a probe built, I think we're going to be still struggling with the science to do what the probe is, and even how to interpret that data, because we may not have the spectral resolution for that. And so there might be some really key science cases that you need to establish, like sort of the foundations for probe science that can only be done with Sophia. So
That would be,
about that.
yeah, no, that would be a great topic of discussion. Like, again, my message to you is like, we don't know how much longer we'll have Sophia, but what can we do to help this field, help the probes or whatever, to articulate and sell this science or help define it.
Thank you again, Margaret.
Let you figure out how to.
Speaker from an area, and let's talk about the interplay between IRSTIG and the support.
Okay. Not. Go back. Okay, thank you. Sure.
Okay, I want to thank the organizers for putting together this great workshop. I've learned a lot here, made new contacts, and also for giving me an opportunity to talk about something that's not in the mainstream of topics here, but I think something that's very, very interesting. I mean, no prize for guessing what it is. I've not made a secret of this. I'm also apologize for pushing every project presented here to see if they can accommodate, the far end of the far infrared for black hole studies. So I'm hoping to tell you something more about this today here. So my collaborators on this project are Michael Johnson and Shepard Dolman from the Center for Astrophysics, who are key players in the Event Horizon Telescope collaboration, and Leonid Petrov from GSFC, who's a VLBI expert, and Peter Kaczynski, who is leading an effort to look at possible space component to EHT. Okay, now coming to the exciting part, I don't need to tell you anything about the first image there. You know, it's probably the most widely seen picture across the globe. And the lower one, though, is less widely seen. And this represents the theoretical expectation of what one might see if one really had an instrument with a very, very fine spatial resolution imaging capability. And what it shows is very fine structure in the form of a nested set of infinite number of rings, which asymptotically approach the event horizon here. And this is not observable with the current telescopes, and this is what you get. Now, as to Astro 2020, this speaks to nature and physics of black holes and event horizons, noted in the report. Now, the image that I showed is made up of a few components that I tried to show here. What you're seeing at the top is what you finally would see. And it's composed of the black hole is at the center. I don't need to go into all of that. An n equals 0 component, which is just a gravitationally lensed image of the emission that is arising in the region near the black hole. And n equals 1 and 2 that we are trying to go after, which form the photon ring, are due to photons that actually go into orbit around this black hole and eventually result in these kind of images that one would see. And there is a very nice video made at the Center for Astrophysics showing this process, and I'm going to play this if this works all right. Okay, what I'm showing here, I think we can stop it. There you go. Okay. Well, so okay, what I'm showing here, the black hole is here, and there is this is a ray tracing simulation made at the CFA. There's light coming from all directions, and depending on how they approach the black hole, some of it would just get gravitationally lensed, basically bent, and form one component of the image that's building on the screen here. And some of this would go into orbit around the black hole, half orbit, come back, and others would go into one orbit and go. And those things form those rings. Depending on the number of orbits, you get different rings. So what? Oh, okay. Building that nice image over there. Having now understood how this forms, we are interested in detecting this photon ring. And given that it's a very, very fine structure, you need very high spatial resolution. And the only way to do this is through interferometry, which is shown on this panel. What we have here is baselines on the x-axis, which are listed in giga lambda. And on the y-axis is what an interferometer typically measures, called the visibility, essentially the correlation between the signals that are received at the two ends of the baseline. And these photon rings produce a very distinct signature, which is a damped ringing. And just the very detection of this damped ringing pattern is a test of general relativity at in strong gravity conditions, you know, photons going into orbit about the black hole. And not only that, the two traces shown here in red and blue, which are from baselines that are parallel and perpendicular to the spin axis of this black hole. There is a difference between those two. So these measurements are able to let you get at the mass of the black hole, the spin, and the spin orientation. And doing all this constitutes one of the most stringent tests of general relativity. And the lower plot simply breaks this down into n equals 1, 2, and 3 rings. And I want to point out here that the there is a demarcation at about 20 giga lambda, below which the image is dominated by astrophysics, jet and accretion disk and all that. And for baselines that are longer than that, you are dominated by the general relativity photon ring signature, and that is the one that we want to go after. So how do we do this? What are the prospects for observing this? Now the lower panel here shows these prospects, which is a slightly different kind of plot, the baselines in the x-axis and the frequency on the y-axis. And in this plot, a given physical baseline shows up as a diagonal line, and all the baselines that are on Earth are within this gray region, and low Earth orbit is here, medium and geo are over there, and the Event Horizon Telescope, which produced that image, is only able to cover this part, which does not come anywhere near the GR region. And you need to either go to higher frequencies or go to space to be able to do that. And today I'm going to tell you that even without going to space, using suborbital, say SOFIA or balloon, you are able to actually get to higher frequencies and reach that region. Okay, now to make further progress with this, I want to introduce the concept of suborbital SOFIA equivalent VLBA ground antenna. Now, much of what we have heard here today focuses on bands where the atmosphere is opaque, but there is unique value in atmospheric transmission windows, which is not recognized. And this is in the context of VLBI, where by definition, you want to have the very long baseline so that you can get very high spatial resolution, which means you're observing your sources at very low elevations, 10 degree, 20 degree. And at those elevations, you have very high air masses. And the moment you go to higher frequencies, these air masses really hit the sensitivity of your ground-based telescopes. Now, if you go to above the atmosphere, then you overcome this air mass issue. Take, for example, SOFIA, which can go to the lowest elevations, it can go to 20 to 23 degrees, where you have 2.5 to 3 air masses. And one can then define, taking SOFIA as a reference or a 2.5 meter size telescope, what would be a telescope on ground which would have the equivalent sensitivity for those elevations. For 345 gigahertz, which is not a band that any of these instruments consider, looking at Mauna Kea, the equivalent aperture that SOFIA or a suborbital balloon-borne telescope would be equivalent to 10 meter, which is a substantial one. And going to 690 gigahertz, we go to the mecca of submillimeter astronomy, Chagnon-Tar, looking at the first octile to quartile, whether the equivalent aperture would be 12 to 20 meter. And even at 230 gigahertz, the equivalent aperture for Mauna Kea is about 5 meter. And these numbers are phenomenal, as you can see. And these are the kind of telescopes that the NGST would want to build to go after, further details of this black hole and photon rings. And I'm coming from these numbers I've estimated for SOFIA, and they are presumably better for balloon-borne telescopes because they can go to lower elevations. I don't know for sure. Now coming from the other direction, from space, the equivalent aperture for a space antenna, if you take a 30 micron surface, would be 4 meter, because a suborbital telescope which has much better surface than 30 micron. So now, how do we observe the photon ring using this? So we need to make a baseline, at least one, with ALMA at the other end. And this way you leverage the big collecting area of ALMA, which does all the heavy lifting. And I'm showing here what this would look like. I'm already showing what the EST can do. And the EST is starting to operate at 345 gigahertz, which comes closer to the photon ring area, but not quite there. Now, if you bring in a suborbital platform, you can go to 690 gigahertz, and that gets you into the photon ring, the general relativity dominated region. And when you're at it, you might as well go all the way. If you go to 950 gigahertz, you're well into the GR dominated region, and you can do very interesting things. And next, it's not sufficient to just have the spatial resolution to go after these structures. You also need the sensitivity. And this plot shows that we do have the sensitivity that is required because of the collecting area of ALMA. So a 10-minute integration with ALMA at 690 gigahertz, 950 gigahertz will produce a few millijansky of noise level, and compared to about a few tenths of millijanskys, this is a viable proposition. Okay, now coming to what hurdles does one face? This is all good. So what problems are we going to face? Of course, the foremost is phase stability. And the moment you have compromised phase stability, you're going to have coherence loss. And this is a pretty drastic thing. So for a path length fluctuation of epsilon, I mean, it drops exponentially. You quickly wash out the fringes that you're after. And antenna and platform movements and jitter will cause these fluctuations, and that's an issue. And the path length stability within the SOFIA antenna and optics is excellent, which is shown by the fact that it achieves 2.7 arc-second diffraction limited PSF at 30 micron. And for a balloon bone example, if you take Atheros at 122 micron, the 12 arc-second is achievable. And compared to the 435 micron wavelength at 690 gigahertz, 690 gigahertz, this is something that's easily done. Okay, then beyond this, one also has to face platform position and velocity variations. And the way to deal this would be through using global navigation satellite systems and an array of accelerometers. And these would allow us to measure the delay rate and acceleration. These are important parameters in fringe fitting when you're going to detect the VLBA fringes. I've done some very quick initial explorations here. A lot of relevant work has been done in the airborne gravimetry community, where they fly jet aircraft at few thousand feet, trying to measure small variations in the Earth's gravity. And they measure the positions of the aircraft and the acceleration to very great accuracy. And the GNSS themselves are able to produce less than about a centimeter of position accuracy. And interestingly, adequate performance is also possible from commercial off-the-shelf MEMS accelerometers, which can deliver 10 to 100 nanoG per root hertz, or 0.1 micron per second square per root hertz. If you integrate that over 1 kilohertz bandwidth, you're achieving, a few micron per second square acceleration errors, and integrating that over 1 second on 1 second sampling, you can get a few micron and a few micron per second position and velocity errors. And compared to the 435 micron, these are excellent numbers, and it seems viable. What are some preliminary requirements? Obviously, as I mentioned, understanding this delay rate and acceleration measurements and the needs of the science needs. Receivers matching relevant ALMA bands, and in the case of SOFIA, there is the forgrade channel 1, which has a band overlap with ALMA band 8. The bandwidth is limited from the SOFIA end, but this may still allow short baseline tests. Other suborbital projects, you're going to have a tailored development which can match the ALMA bands well. And of course, you need to provide these instruments with frequency and time standards and VLBA backends. And a partnership with ALMA and the NGEST will also be required. And finally, I want to touch upon another important requirement, that simultaneous lower frequency observations would be required. This is because you want to take advantage of the strong astrophysical signal at low baseline region, which is where the EST and the NGEST operate. And you can get initial solutions for VLBI by detecting the astrophysical signal, which will narrow down the range over which you will need to search for fringes at 690 and 950 gigahertz for going after the photon ring signal. And here is a path I propose. Wet and solidify these estimates. This is all very preliminary. I'm just putting out a concept here to develop the concept further. And accelerometer studies and VLBA data reduction methods which can incorporate such accelerometer data. And short baseline proof of concept testing before you go after the photon rings themselves. And in the case of suborbital balloon projects, of course, there is telescope development involved, but then there's a lot of experience there. I may be going out on a limb here, but that gets the best fruits. I want to end by saying that, hopefully I've given you a feeling for what all this is about. And hopefully I've convinced some of you that suborbital ALMA VLBI can enable transformative advances in black hole photon ring studies. And this is within reach, and it's possible in the near term. And this can be a stepping stone to submillimeter space VLBI. I'll end there and take any questions. Thank you for putting up with me.
And making images of this, well, it's really very complicated structure. You need really good UV coverage.
Yes.
Have you looked at that with an airplane and possible flight paths and things like that, and where antennas are located?
Okay, I've not looked at any of that, but then here, this is a very simple experiment in which we are not trying to construct any image at all. We are actually not even attempting to measure the phases of the visibilities. It's only to produce the ringing pattern as a function of baseline length. And it essentially is scratching the surface so that you can now say that, yes, there is this photon ring and its signature is there, and one can do grander things with, bigger facilities in space, et cetera, et cetera. So that's the idea of this project. But I mean, I'm interested in all sorts of feedback, by the way. I mean, please talk to me here or later. If people think this is crazy, let me know.
Hi, well, it's certainly a fascinating idea to consider. I just want to reiterate, as I mentioned in my prior talk, for heterodyne spectroscopy, what you care about is aperture. You don't particularly need space to do this experiment. You just need, I guess you're going to space to maybe get a longer baseline.
Right.
But if you were, I mean, I think you'd have to start off maybe at suborbital, because again, you don't need the expense of going to space for this particular thing.
Right. Okay. So in fact, I should point out here, Gary was the first person to put out these ideas. You know, he was trying to get the Origin Space Telescope to incorporate these possibilities.
Oh, sure.
Yes, I'm sure many of you know about this.
Yeah, and that was a 6-meter aperture. So that's
Right.
an example, quite different than
Yeah.
we have
So
to
there are
see.
multiple things here. One is that if you have the very long baselines, then you get better spatial resolution. But in low Earth orbit, because every 90 minutes the orbiter can go around, UV space can get filled very quickly, and you get very good UV coverage, and you can go after dynamic phenomena much more robustly than would otherwise be possible. You see that there are those advantages that you get from.
I see. So if you have,
Unless Gary wants to add something.
right, okay, no, right.
Okay.
I'm just pointing out that you don't need a full telescope.
Oh, no, we don't need cold telescope. Yes, absolutely. That's right.
Yeah, a low Earth orbit telescope will do the UV coverage, but it won't improve the angular resolution much, because adding 300 kilometers to the radius of the Earth doesn't make a big difference in terms of spatial resolution, but it does fill in the UV plane. The question I had is integration cost.
Right.
The image that Shep and the EHT team showed that wow the world, those were data taken over 5 days.
Right.
With Sophia, you'll get maybe 4 hours at a time.
Right.
Towards like M87. So the question is, can you get the signal to noise that you require with a 2.5 meter aperture in a Sophia plot?
Right. So yeah, so the calculations show this, that you can. So okay. So one is not trying to construct this full-fledged image, right? One is just only trying to sample. Right.
No image.
So not an image. Not only that, we want to do something like what the CMB people do, the band average, the acoustic signal, right? I mean, where you average band. So here you can average UV spaces so that you can get the signature, and the signal to noise ratio can build over time. And the calculations that Michael Johnson made in this paper, where all this the photon ring stuff was put out, it shows that a 4-meter antenna in space with ALMA single baseline at 690 gigahertz would detect this in 10 minutes. And a Sophia 2.5 meter or a suborbital balloon borne 2.5 meter is equivalent to about 4 meter, 30 micron surface antenna in space.
For 4-hour on target integration, let's say, roundly speaking, for Sophia would be sufficient signal to noise.
Yes, yeah. I mean, that's for getting one measurement, you know,
Yeah.
one UV.
Yeah,
And of
I
course, you need to
understand.
get, yeah, right.
Last question there.
It's a naive question because I'm not a thermometer. Does the suborbital or Sophia measurement with ALMA have to be taken concurrently for the measurement? Because that would imply that Sophia or your balloons have to be in the vicinity of that part of the Earth if you're looking at M87 or something else. Same time is the old time.
Yes, this has to be taken at the same time. So it shouldn't be in the vicinity, actually. You want to be very far away so that you can get a long baseline. Yes, so they need to be taken simultaneously. That's right. That's how it works. I can talk to you more about it later if you like.
Thank you again.
Thanks.
Thank you. The last question of this, the last talk of the session is from Bernard Schultz, who is the Deputy Director of Sophia, and is going to talk about Sophia instrumentation.
Do you want that one or the hand?
I take this.
That also points and stuff. But you can use the-
Okay, hello everybody. So my name is Bernard Schultz. I'm the Deputy SMO Director, so I'm representing the German component of Sophia. And well, I want to tell you about our instrumentation effort that we started on the German/European side. Basically, after the NASA Sophia instrumentation roadmap came out about a year ago, Margaret showed a little bit of this. The encouraging thing there was that this was a 10-year vision. So the problem is always on our side that funding agencies tell me, well, look, we don't know whether Sophia will still fly when you are finished building your instrument, so we cannot give you the money. And the typically instrument development period is about 4 to 5 years. So this is catch-22. Now, with a 10-year scope that was in this roadmap, we felt that, okay, this is a good opportunity here to rally the troops and see whether we can actually get an additional instrument done on the European side, in addition to that instrument on the American side. And so I'm going to talk about this a little bit here. So we organized 2 German-European workshops. The first one was to establish the science requirements. The second one was to determine the technology status and the instrument options. And then I'm going to finish with conclusions. So this is the overview of the talk here. The science requirements workshop was done in July last year. We had a big interest, 231 registered participants, 3 days. This was virtual, of course, because of COVID. We had 56 presentations. The main themes, guess what? This is what Sophia is good at: interstellar medium PDRs, shocks, star formation, astrochemistry. These are the things that Sophia does well. Interesting to note also that a third of these presentations were actually extragalactic. So there's a big interest also there in the far infrared. The main requests here on the right, you see a table. I'm not going to go into detail here, but we distinguished 63 science cases, and then we looked a little bit at the statistics, who wanted what. The main request was really high resolution spectroscopy in the mid and far infrared. I mean, really high resolution, like heterodyne. the people were willing to trade spectral resolution for sensitivity, which you need, of course, for extragalactic work. But then also calorimetry in the far infrared was important. Broadband photogrammetry in the far infrared specifically, and then specific lines, and also time sampling. Now, after these science inputs, we got a second workshop, which was done in November. This was a more specialized one for those who can actually build instruments, and even there, for such a specialized workshop. High level of interest, 156 registered participants. Again, we did 3 days. This time we had a little bit more time per presenter. The main themes were airborne platforms, heterodyne, direct detection, and instruments and funding. Now, let's just talk quickly about the heterodyne technology. The general receiver architecture for a heterodyne is well known. It doesn't change so much. You have telescope optics, you have a local oscillator, you mix these, get it through the optics and then into the mixer, and then you amplify the difference frequency. There are various solutions, of course. Herschel IFI was already flown, it was a very advanced instrument, but meanwhile technology has increased its potential, and we are talking now about arrays of heterodyne receivers. I'm not. This is just so you will see these slides. You can pick it up later from the internet. I just left a few references here. I'm not going through all of this. Just to talk about the main components of feed horns is pretty well understood. Mixers, there are 2 types of mixers: the SIX mixers for frequencies below terahertz, hot electron bolometers for frequencies above a terahertz. There is development in bandwidth. Typically, it's 5 gigahertz bandwidth, but there are new materials where you can increase this. The local oscillator that provides a mixing frequency is always important. The question always, how do you bring in this mixing frequency? The power of these local oscillators is always an issue. There are 2 types. The splitting point is 2 terahertz, and then another item of research is, of course, a back-end spectrometer, where you analyze the frequency, the intermediate frequency, then, and those electronics require a lot of power. On SOFIA, we do have this power, so this is quite great. Actually, works quite greatly on SOFIA. However, if you go to 100 pixels, then you need to develop this more, because you need to reduce the power consumption per channel. There are many issues when you want to have 100 pixels. So challenges, micromachining, miniaturization, LO coupling power, and so forth. This was discussed at length during the workshop, and probably a stepwise approach, modular, where you already anticipate an extension to 100 channels, but maybe start with a smaller number, is probably a good way to go. So the idea how such a current network would work is relatively clear. It can be done. There is a challenge with 100 pixels, clearly, but it appears feasible. And one needs a simple reproducible design. There were various suggestions how to do this. The idea of a kind of a tuned, optimized front end for just one frequency, but 100 pixels is one of these ideas where you say, okay, I do the O1 line with 100 pixels, and then I go to C2. So for that, I just switch out the entire front end, but keep the back end spectrometer. So the expertise is still there. Funding is needed, of course, right, in order to do this. Important point here I want to make: high resolution spectroscopy. This is the niche for airborne observatories, right? SOFIA, balloons, you can really do this. SOFIA is particularly good because it has these big power reserves and also weight reserves. The residual atmosphere is here as an obstacle, and there's only a moderate gain that we can get from a cool telescope. So this is when we talk about a probe mission, this is really not something that we can gain so much with a space mission. The direct detection technology is even a bigger zoom, and again, this is a crowded image. I'm not going through all this, just saying the kit detectors. Okay, so first of all, we get much larger pixel counts here that are possible. High sensitivity, low spectral resolution, typically not as high, certainly as heterodyne. In particular, also we get no quantum noise penalty. This gives us higher sensitivities. The kinetic inductance detectors seem to be the most promising detector type in that area. There were also instruments proposed, the PVLS upgrade, for instance. The test detectors were also discussed a little bit, but we didn't have much expertise there, at least in our workshop. What was pretty interesting was a continuing the development of what flew on PUCs as imaging detectors. Those are semiconductor bolometers, and these are now polarization sensitive. So these are small antenna structures, really, that little dipoles and stuff. And in the end, there's also something called electron bolometers. This is a new thing. Unfortunately, the new political developments, this is collaboration with Russia is certainly a little bit of a problem. Anyway, looking at instrument ideas with direct detection technology seems to show that the FIFI-LS upgrade would be actually something we could consider low-hanging fruit. It would need something like $4 million for doing this. The proposals had already favorable reviews in a previous round of instrument proposals, but it was not really, there was no decision really at the end. Also, of course, a Hermes continuation, which an instrument that was being developed but not finished because of issues. That is also a possibility. A lot of hardware is already there. Also a modular approach where you take just pieces of what has already been done and go for very specialized science bases like HD. You could do this and then kind of modularly build up the instrument again. There's also the idea of an infrared channel for the photoplane imager. That's comparatively very cheap. And other things like the Ebook derivative would also fly in SOFIA, do polarization and 350 microspectral mapper. Anyway, many options. We felt that we need another round of reiteration with science on this one. Now, coming to airborne platforms, we had lots of presentations about airborne platforms. This was an inclusive workshop. It was airborne, so it was not only just about SOFIA. Of course, SOFIA was presented, and then co-pilot, BLAS, Astro, the Sunrise mission is a UV mission, but these guys in Germany have a lot of experience with flying a balloon. I think only Gusto we didn't have, but yeah. So the discussion was long and on this one, and in particular the question how you do an observatory with these kind of observatories came down to the point that, well, SOFIA is really a working observatory that produces data on a regular basis. It can respond quickly, etc. So there are quite a number of advantages for SOFIA. Of course, balloons have their own niche, and that's also important, right? In particular, they allow higher altitude, so you can do things you cannot yet do with SOFIA because of the rest atmosphere. You can also do long observing time things, but generally, the big problem was always how do you land a balloon safely? And the answer at this point is no, you don't. You plan for 100% loss. This is what these teams told us consistently, that you know, you really may lose everything and then you just build it again. Also, when you talk to everybody about, okay, cadence and when do you fly? People talk about, yeah, in 2 years we have another flight opportunity, and then we wait a few months for the good weather conditions, and then we fly. So it's a completely different paradigm. You know, so you can do very important, very interesting missions, but it is not like an observatory where you go, okay, now we observe, oh, a supernova has happened. Now we go and we fly. So this is just not happening. So what do we do? Balloons are great for focused high altitude missions. There's certainly a long ways still to regular observatory operation. I mean, this has been proposed, right? But it is hard. And new airborne observatories will need safe landing and mobility, so propulsion or something like this. There are ideas about this. There's also a study by the Tech Institute about airships. Generally, 65,000 feet are reachable with these. And, you know, this would be a great SOFIA successor. And considering development times, we should start now thinking about this. Ultimately, SOFIA is working, well performing, way better than what the decadal survey tries to make us believe. And we still have 11 years of its 20-year operational lifetime left, if we just consider the technicalities here. We can build new instrumentation, but we really need a new contract with the science community, with all the stakeholders. Everybody has to agree on a lifetime of SOFIA, and then we can also build new instrumentation, right? And then currently this on-off, and it has been discussed on-off 1 year. We're not succeeding with this, right? And so any funding, I think not even only European funding, needs a kind of a lifetime of something like more than 5 years. So everybody agreed in these workshops, keep SOFIA flying. We really need this. Stopping now is like stopping Herschel after 2 years. It's really like this. And so we need to agree on remaining lifetime, provide stability. And we should also spend more budget on the upgrades, because this is what SOFIA can do. It lands every morning safely. And well, we also should prepare for successor now. I think that's it for the moment.
So at the end, you talked about a new contract with the scientific community and general agreement that this meeting should keep going. Did you have discussions or ideas about how to, implement that and actually feed back to the community and get that consensus moving? That's the hard part.
Yes, well, it really comes down to politics. You need to invite all the stakeholders on the table. So in this case, stakeholders are the scientists, certainly. This is NASA, this is DLR, so German NASA. But then we really need the scientists to drive this and provide this backing. I mean, we have strong support from the German Council of German Observatories, for instance, right? They are writing letters in our support. And this represents the scientific community, but I think we need more than this, right? We need really proposals. We need people who stand up and make SOFIA more known, and also talk about the consequences of losing this working observatory. It takes years to come to a state that we have now with SOFIA. We had tremendous progress in the last 2 years. But this takes time. There are time constants involved. So some of the changes that we introduced in the program, they're many years old, but they take time to take root. And so all of this together needs to be taken into account. I have no gold rule now how to implement this, but we need to keep talking and talk about the consequences of not having Sophia.
Okay, thank you very much for your talk on this. You correctly point out that Sophia is a function of observability, right? It's not like one. For something like what I proposed, which is of course off mainstream, such a thing is very attractive because you don't have to build from scratch. All you need to do is put an instrument on, or maybe a super instrument. So, is there a pathway for funding such development? I mean, does anything like that exist? If one wants to do it, where does it go?
You're talking about your proposal now, or?
Yeah, I'm talking about my proposal or something else that someone else might come up with.
Yeah,
Right.
right.
I mean, is there a path at all for new development for Sophia?
Well, yes and no, right? So, okay, I cannot speak for the American side. I'm sure there are, I mean, so NASA has, of course, programs to further instrumentation. On the German side and the European side, we actually found we have a gaping hole in there because we have funding opportunities for the ground, we have funding opportunities for space, but everything in between. We have nothing for balloons, we have nothing for Sophia in terms of instrumentation funding. So this always has to go through separate routes. For instance, the GREAT instrument was such an example. They made a science proposal to the DLR, to the DFG, so German funding, anyway, the German funding agency. And they, they said, okay, we want to do this great science. And by the way, in order to do this, we need to build an instrument. So give us money for that. And it did actually work. And this is how we came to this nice instrument. But yeah, we have a structural problem.
Thanks for a nice summary of the situation. And if you'll forgive me, I don't have a question, but prompted by a statement that you made on one of your slides, I'd like to suggest something for discussion this afternoon as we think about possibilities. All of the questions for this afternoon. But the comment that you made was that balloons were relatively inexpensive. And what I'd like to suggest is that one criteria that should always be calculated for any kind of an experiment. Not the only one, and I'm not saying it would get all the weight or anything, but one thing that should always be calculated is what the cost is per observing time, per observing hour. It can be an illuminating calculation. It's valuable. It's valuable for space missions as well. To give you one example, the observing efficiency, the amount of observing time that you actually get on sky varies quite a lot from one space mission to another. And that actually, by a factor of 2 in some cases, affects the cost. But it's a good thing to calculate all the time. I just want to make that suggestion setting up this afternoon. But thank you for prompting the thought.
Yeah, no, thanks for the comment. And I just wanted to also say that, you know, this comparison that Margaret showed, that with Herschel, where you actually find, oopsie, we are actually within the first 8 years, Sophia per observing time, you know, the hours per proposal are pretty much the same. And for me, it was actually a little bit astonishing, but yes, you know, so.
It can be quite illuminating.
Yeah. Okay.
Thank you so much. And thank you again.
Thank you very much.
So, keep you on your toes and wake you up. We juggled around, we didn't juggle around the schedule. The schedule today is different than previous schedules, which is we're going to go into a coffee break, refresh yourselves. And at 10:20, we'd like to come into the small groups to talk about the 5 questions for today, which are related to Sophia and other things. And then we're going to have some more talks at lunch and whatnot, and then we'll come back together towards the afternoon to have a bigger discussion, summarize and try and figure out what we think of all this. So, yeah, so get some coffee, refresh yourself, and then go into the small groups. Thanks. They're both work, you gotta get it. This is the same psychology. Tips. Say you have 2 minutes left. Well, they just have no sense of what 2 minutes is. If I set a timer and it's like actually 2 minutes, they freak out. They're like, that wasn't 2 minutes. Ready? I'm happy. I'm waiting for the other groups to break up.
I think we're just chatting now.
Okay. You want to go over that? That's an announcement. Let's see. Okay, everybody, let's take our seats. I have to say, one of the big successes of this workshop is it's impossible to get you guys to stop talking. Okay, so looks like by the process of elimination. That's good. Our next talk is going to be by Jordan Weaver. He's going to tell us about cool stuff happening in this.
All right. Hello, I'm Jordan Wheeler. I'm a postdoc at NIST Boulder here. I work in the MKID group. Today I'm going to tell you about new kinetic inductance detectors that are direct absorbing kinetic inductance detectors. And we're working on these as a potential upgrade for the Hawk Plus instrument on SOFIA. So I guess, this is competition sensitive. So if you're my competition and you're in the audience, oh well. If you're not, maybe don't tell them, but oh well, I'm giving a talk, so the information's out there. All right, let's get started. Next.
Oh, use the mouse to click on those.
Okay, so first I have to talk about the thing that I'm not going to talk about. And so this is our past work with kinetic inductance detectors and NIST. Our bread and butter is doing feed horn coupled kinetic inductance detectors. We've done that for several projects. We're still doing it for other projects right now. The first here is BLAST. Phil told us a little bit about that on Wednesday. The highlight of BLAST is that was one of the highest frequencies arrays we did at 250 microns. So that's a picture in the top right of that. That detector wafer was on a 4-inch wafer. We generally do 6-inch fab now, but that had 2,000 detectors. We've also delivered arrays of kinetic inductance detectors for Toltec. That's longer wavelengths. Those we delivered with NIST silicon micro machine gold plated feed horns. Those are really nice, precise metallized feed horns. And then we're also working on a bunch of arrays for the CCAT collaboration. We've delivered one, and there's many more in the future to come. And that also includes an array at 350 microns, or 1 to 3 arrays at 350 microns. And those may have as many as 20,000 detectors on one 6-inch wafer. Kinetic inductance detector technology is constantly evolving. So just highlighting one aspect of that in the bottom right here. This is a plot of 1/f noise in kinetic inductance detectors. So the blue, green, and the red are titanium nitride inductor. And titanium nitride is a great far IR absorber. That's why we like it, because it's very resistive. But it has 1/f noise in the inductor, which is annoying. But we do find that if you go to lower TC titanium nitride, that 1/f noise gets better. It also makes your detector much more sensitive. Now, if you have an application that requires ultra stability, then you really just want to go with an aluminum kinetic inductance detector, because those detectors can have no 1/f noise, assuming that you engineered your capacitor correctly. Okay, but now what I actually want to talk about today is a new type of kinetic inductance detector for us, which is a direct absorption kinetic inductance detector. So the text on the left is kind of just giving a few of what we think the advantages of MKIDs are, specifically for Hawk, but also just generally. Most of the people that put kids in their instruments end up doing it because they want the most pixels possible. Also, MKIDs, this fab is relatively simple and it's robust. It could be just a single layer of fab. I think the real power of simple fab is that it actually enables rapid prototyping. So instead of wasting Mike's time making some complicated detector with 10 layers of fab, I can waste his time. He can make me 10 different detectors. All right, and then MKIDs are also, they're more lenient in terms of saturating, right? There's not going to be a power level where they're just rendered totally inoperable. That doesn't mean that they work as well at super high loads. You'll potentially have more crosstalk or more amplifier noise, but you're not going to launch your satellite and discover all of a sudden you can't do anything with them. Okay, so now on the figures, so the top right is showing the architecture of this type of detector. And starting on the left here. So I'm an MKID guy, not a TES guy, so I don't want to default to doing something with a membrane. So these are backside illuminated detectors on a thick 500 micron silicon substrate. Okay, so now once I put them on the silicon, if I don't want to throw away 30% of the light, I have to AR coat them. So that's the very top of that figure. These are just totally planar detectors. So it's actually relatively simple to do a metamaterial AR coat to get that AR coat done. Okay, so now once we've got the light into the silicon, it propagates down to the detector on the back side here. And so the schematic of the detector is shown on the very right there. And for MKIDs, your inductor often does double duty. It acts as the inductor in your microwave circuit, but we also use it to absorb the light, to be the far IR absorber. So basically, we just take our inductor, we wind it all around the focal plane to make a resistive sheet in either 1 or 2 polarizations. Okay, so if you make a resistive absorber like this, basically if you had a sheet that was 377 ohms in free space, the light that impinges on it, 50% of it will be absorbed. If you put a quarter wave backshort below it, then you can absorb 100% of the light, excuse me, at one frequency. But these detectors want to be really wide band, 1 to 6 terahertz. So then you're worried that you'll have a halfway at some wavelength and you'll get no detector efficiency. But what we find is if we use a sub-quarter wavelength back short, we can actually still, oops, moved on somehow. We'd actually still boost the detector efficiency over this very wide band. And so the result of all that together is, in this bottom right plot, where we're getting greater than 85% detector efficiency across the whole 1 to 6 terahertz band. And even better than that, because it's optimized, even better than that for the Hawk bands, because it's optimized specifically for those bands. So we've taken something that, used to be limited to 50% absorption efficiency and boosted it up. So we heard earlier from Margaret, up to 4 times improvement in polarimetric mapping speed. And I say, I can do better than that. All right, so now on to some results and things. So here's some AR coding design. So when I say I'm going to do 1 to 6 terahertz, I guess I apologize. Maybe this conference I should have relabeled everything to microns. Everything else I see is microns. So 250 microns to 50 microns. And I say I want to do an AR coding for that. You might say, oh, that's too large of bandwidth. And you're not totally wrong, but we can be clever about it. So here we have a single layer AR coding. And what we can do is we can optimize for the low frequency bands to do a quarter wavelength back short. And then we can actually capture the 2 high frequency bands of Hawk with a 3/4 wave back short. The expense here is that we've done optimally bad here for the middle band. It's still better than a membrane solution, but we can do better. So that's what we do with the 2-layer coding here. Say, we have 1 more degree of freedom. Can we, oops, my slides are moving along on me. Can we fill in that gap? And the answer is yes, we can. And we can do quite well then for all of the bands here. Okay, so that doesn't really mean much unless it can be made. So, I can come with a design age of success, but then I have to ask the fab guy, hey, can you actually make this design? And so I asked Jim, can you make this? And he goes, I don't know, I'll just try it. All right, so here's his try. So some pretty pictures on the left of the 1-layer AR code design. And it looks pretty good. So now this is a 10 micron pitch, 20 micron deep holes with 2 micron wide walls. And so then we sent this chip after he made it off to our colleague at Gaithersburg, who has a warm FTIR where you can measure this stuff. And that's what this data is showing on the right. The warm FTIR, it's not the best in terms of signal noise, but it does allow us, it's great for this rapid prototyping. So the nominal design is shown on this plot in red. And then green is when I take the measured parameters from this cross section and plug it into the model. And then the data with 2 different normalizations is in orange and blue. And basically we think, oh, well, it looks like our AR coding is working exactly how we expect to the accuracy we can tell from this measurement. Okay, so then Jim told me, I'm going to go to Canyonlands and do some off-roading and think about how to do the 2-layer edge. And then he came back and he gave me this. So he was clearly inspired by the great outdoors. That's really beautiful 2-layer design. So now the top layer here has 1 micron holes on a 1 micron walls on a 10 micron pitch. This is very small stuff. Okay, and then now we have the results from the warm FTIR on this 2-layer fab. And again, we have, red is the nominal design. Green is what we do when we measure the outcome of this. So on both cases, we missed a little bit in terms of the depth of the AR coding. And that's fine though, because we're basically specifying that we're going to do this with SOE wafers. But SOE wafers have this huge lead time. Oh, my slideshow has some old timings or something. SOE wafers have a huge lead time, and we're not patient enough to wait around for that. So he's just doing it with a blind edge. But basically, we see that the XY tolerancing is really good, and that the AR coatings work exactly how we expect. And once we have the SOE wafers, we'll get the Z tolerancing spot on too. So this makes us really confident that we can do this 2-layer AR coating, so much so that I'll probably never think about the 1-layer AR coating ever again. And we're proceeding with our next test devices to do the 2-layer coating. So I think this is really exciting because this is some of the highest frequencies that this metamaterial AR coding things have been done at. Okay, let's talk about the detectors now. So we're through the AR coating, through the silicon, onto the detector on the backside of the substrate. And so this is what a pixel looks like for our detector. So basically right now, we're just filling 80% of the pixel with meandered inductor that acts as an absorbing grid. On the right is the interdigitated capacitor. We use that to tune the resonant frequencies of the detectors for the readout. And then on the bottom is the microstrip feed line. That microstrip feed line actually uses that small back short, 19 micron back short as its ground plane, which allows it to be really small and not really affect your filling factor too much. And then on the left here, we have a zoom in of what kind of the unit cell of this absorber looks like. So using that technology we use for our feed horn coupled kinetic inductance detectors, where we use tinitride as the absorber, and it's great. It's very resistive, maybe too resistant. So we actually will cover some of the tinitride with thick aluminum to short out that resistivity. But this is also really great because now it means that our absorber design for optical efficiency is decoupled from the line width here. So now I can get the same absorption efficiency, but I can change the line width from 0.7 to 4 microns and thus change my active detector volume by a factor of 32. So I can tune this detector sensitivity how I like. Okay, that's the single pole version. A quick just diagram of the dual pole version. The dual pole is the same idea, but instead of one grid in one dimension, you want to have two overlapping grids in both dimensions, but you can't overlap your inductor for your kinetic inductance detector. So you just do something clever like this, and it absorbs quite well, where you basically approximate a grid in both dimensions. Okay, so we did some initial testing right away with what we're most comfortable with. We're used to doing feed horn coupled detectors. We have that test set up in the lab. So we quickly made a fab that basically has a feed horn coupling mechanism and then has basically the whole pixel you'd use for Hawk over on the right. So that approximates the total volume, the geometry of the microwave circuit, and all of that. And that lets us kind of dial in, what do we actually need for a detector volume, for sensitivity? Is our TC coming out right? Is our microwave design correct? And all of that. And so here are some initial test results for that. So we targeted the TC at 950 millikelvin, came out at 975 millikelvin, great. There's a triple R value for the tinitride of 1.3. So this says that basically the tinitride will have the same resistance warm as it is cold, which is really great for us because now we can send it to our FTRR guy and he can measure the absorption of these detectors warm. The QIs were great, dark QIs 100 to 200,000. QIs under loading level were also good. Microwave frequencies were on target. We had one problem, which is the aluminum got over-etched here compared to the tinitride. That's a problem because if you break quasi-particles here in the nominal tinitride, they can diffuse over here to this tinitride, but the microwave circuit will ignore that because the current will just go through the lower inductance aluminum. That's okay though, because this is why we do these test fabs to figure these things out. So here's just some initial test results in terms of sensitivity. The 1 micron line width version that we made was basically within a factor of 2 of where we wanted to be in NEP. Should be totally there, maybe more so once we fix the aluminum over-etch problem. I also centered the horn over the Hawk style grid absorber, and that worked as expected too. So that gives me confidence in the electromagnetic simulations that they're working correctly for this kind of thing. Okay, so now we're currently fabbing the next round of prototype detector chips for this. So these are going to be 8x8 test pixels. That's just nice small size we like to do lab characterization with. So 64 pixels total. And you can see the detector chip here on the left. And then it has this back short chip on the right that looks like a puzzle piece. And that we put on the top of the detector chip. And the puzzle piece allows us to precisely align it to it, but still leaves us room to get our wire bonds down to the detector chip. And then we're also doing some 512 pixel networks just to validate our readout muxing at near the current levels that they would be for an instrument. Okay, so these are being fabbed right now. These are some pictures Mike sent me like last Friday of the devices. So this is the dual polarization device on the left. And this is the single polarization device on the right. It's looking great. I can't wait to test them. Hopefully these just go in the cryostat in front of the black body next week. All right, so I'll just bring that to my conclusions here. This is a promising new detector technology. So this is going from 250 microns to 50 microns. Direct absorbing is kind of neat, works almost like a CCD. We're thankful for Sophia to be, forward looking to the future to invest in this kind of detector technology potentially. And just really excited about it. And I think even beyond 50 microns, this detector technology can go even lower in wavelength. And I guess I'll just give you the sales pitch. We're the novel devices group at NIST, and we may not have a solution you need right now, but come talk to us and we'll think about it together and try to come up with a realistic solution to meet your needs. And MKIDS, the real power of MKIDS is rapid prototyping. So just because it doesn't exist yet doesn't mean it can't exist on a relatively short time scale. And I'll just end and say, thank you very much for your time.
Well, apologies, I should know more about this, but you mentioned there rays that are sensitive for both polarization directions. Are the single pixels
They're
sensitive there, or do you still?
They absorb both polarizations. They don't differentiate between the two polarizations, just to be clear.
Okay.
So the Hog instrument has a polarizing grid, so it really only needs a single pole detector. But if you don't want to do polarimetry, you would want a dual pole version. Our feed horn coupled kinetic inductance detectors are naturally polarization distinguishing.
Well, I mean, this is really cool because of course MCAD will be in long wavelength and to show that you can get them to these far infrared wavelength that gets it really, that's very exciting. You said your prototype detector has 64 pixels. Like part of the other issue we have with detectors in this wavelength range is how big can you make them? And so how big are you anticipating making them? You could say for Hawk Plus, but how big can you make them, period?
Yeah, so we basically just fab on 6-inch wafers and pretty much just fill the entire wafer with detectors. That's actually bigger than the optical area of Hawk. But for Toltec, they just said, oh, let's stuff in as many pixels as possible. So basically the entire wafer is filled. CCAT, they have hexagons so they can stack them together, but one wafer fab is just one 6-inch radius circle.
Not to have you give away any trade secrets or what have you, but I'm just curious, since far infrared detectors really is a select niche area because there isn't a commercial application besides our lovely telescopes. Were you working in novel technologies? Are you seeing emerging, we heard a comment the other day about security systems using radar. Are you keeping your eye out on other sources so that this might influence new detector technologies that now you can bring to the astronomy community?
Yeah, well, NIST has its own security camera that's mostly been sitting dormant for a while. So, I mean, this would be a great application for something like that because the detectors are relatively simple. You don't have to build the whole feed horns. They act like a CCD. So, I mean, on that front, the commercial front of far IR detectors being used for things that aren't astronomy is mostly being pushed by the people that originally used them for astronomy. So it's usually us informing that way rather than the other way. Not sure if that answers your question correctly or not.
Quick one, I might have missed that. So you showed on the first plot the issue with the time nitride. So are the inductors time nitride or aluminum? This one.
The inductor is tinitride, and then we put thick aluminum on top of it to hide a lot of the tinitride, just to control the resistivity, basically. Right, if we left it all as tinitride, we'd have too many ohms per square at a couple effectively. So we just put patches of aluminum over a lot of the tinitride. And I guess if you look at this dual pole version, you can see that the pink purple here is the aluminum. We draw it a little oversized, and then all this tinitride is here. But the only active area of the detector in terms of kinetic inductance is this exposed tinitride.
And so does that still show the one of our issues or is this kind of the
Yes, because the active area is the tinitride. It will have 1/F noise. So that's basically all tinitride we do now. We like to push the lowest TC because that makes the 1/F noise the best. So this was 975 millikelvin TC, which is lower than things we've done in the past, but still high enough for the Hawk Plus base temperature.
Let's thank you again.
Okay.
Okay, so this is an instrumentation session, and I'm going to bring you back to science for the next 20 minutes, maybe even less. And I'm part of the IR STIG, but this is really a talk from the scientific point of view, and I'm gonna try to cut to the chase and go back to requirements for what I think are again requirements for a future far infrared probe. And in particular, I'm going to advocate that although spectroscopy is fantastic, we have been talking about spectroscopy for the last couple of days, imaging is not that. And now there is still a lot that should be done and could be done with imaging, and lots of scientific questions that need to be tackled with imaging. So in particular, I'm going to talk about the core mass function. And I'm going to start with this diagram. And we have seen different incarnations of this diagram during the last couple of days. And in particular, we have been focusing, and for very good reasons, on going to try not to, okay. We have been focusing on these two phases, which are the protoplanetary disk phase and the debris disk phase. But what I'm going to argue is that if we want to understand how planetary system form, we need to understand also the preliminary phases, which is basically the collapse phase. So basically how a dense region in the ISM and dense and cold region in the ISM collapses to form the protoplanetary disk. So, and this is basically what I'm going to talk about exactly. So the core mass function, so the description of how basically the masses, the statistical distribution of masses in prestellar cores, and how the mapping between the initial mass function and the core mass function. So I'm going, this is a disclaimer, this is not a full-blown talk about the core mass function or the initial mass function, but again, it's mostly about requirements for a far infrared probe. So to talk about the core mass function, I need to talk about the initial mass function, which is mostly known because it's been studied for many decades now, and it's what is mostly known. So first of all, I want to emphasize that the initial mass function is not an observable, but it's a statistical description. So it's a statistical description of the mass distribution of a newly formed stellar population. And there are two main descriptions that are used in the literature: the Chabris initial mass function, which is basically a log normal distribution followed by a power law, and then the Krupa IMF, which is basically a continuous set of power laws. But the important point is that basically for masses above roughly 0.2 solar masses, these two descriptions basically are in agreement. For masses below 0.2 mass functions, there are still many uncertainties. Now, the questions that everybody asks is the IMF universal? Now, until few years ago, everybody claimed that yes, the IMF is universal. But over the last decade, there's been more and more indication that actually this is not the case. And both from galactic studies and from extragalactic studies. From the galactic point of view, we know that there are outstanding examples of IMF that don't follow the common prescriptions that we just talked about, like the Taurus molecular cloud or the Western 1 cluster of the quintuplet, the arches. And one may say, well, but these are cases in which there may be mass segregation, so you are not actually sampling the entire IMF, you are actually biasing your study towards a part of the basically higher masses or lower masses. But there is indication also looking at extragalactic studies, in particular elliptical galaxies, that again, the IMF might not be universal. And so from elliptical galaxies, we find top heavy IMF or bottom heavy IMF. So basically IMF where there is an excess of high mass stars or low mass stars. So how does this connect to the core mass function? So to the preliminary actually stages or phases of the collapse. So over the last, I would say 15 years, we have started studying the core mass function. So basically, again, the distribution, the statistical distribution of the masses of the cores that are going to form stars, and how this can relate to the initial mass function. And Herschel in particular has provided one of the most outstanding probably cases that we know to date, which is in the Aquila Rift. So this is a star forming region at roughly 260 parsec. The area that was mapped is 11 degrees squared, so it's a large area in the sky. And what was found is the curve that is here in red. So this is the core mass function that described the prestellar cores. And basically it was found that that the core mass function in the Aquila Rift can basically be described in a very similar way to the initial mass function. So with either a Krupa or a Chabris, but shifted to higher masses. So basically, how can we explain this? We can basically simply explain this by assuming a 30%, roughly 30% efficiency and and a constant efficiency at all masses. So if we say that basically when the cloud collapses and 30% of the cloud that collapses goes into stars, then we can explain the shift. But there are lots of questions that remains, because there are lots and lots of limitations. So this is one example. And we don't have many cases that were studied by Herschel. And moreover, Herschel studied really cases very nearby. And these are basically dominated by low mass stars. And ALMA recently has been trying to improve the situation. So there is one program, which is the ALMA MF, that basically is trying to improve the situation. So by looking at 15 high mass star forming regions up to 5 kiloparsec. But again, we are talking about small sets of observations. So the outstanding questions are, so does this, the core mass function map into the IMF? Is there a one-to-one mapping via this 30% efficiency at all masses? Moreover, how does the environment impact the core mass function? So what are, for example, the roles of metallicity and feedback? So metallicity and feedback can have lots of effects, and they can go in all directions. So they can create a bottom heavy or top heavy IMF, and therefore also and actually so core mass functions. Another thing is that from the preliminary results from the ALMA IMF program, we can see that actually this mapping that I was talking about between the CMF and the IMF seems to break at high mass function, at high masses. So the core mass functions seem to become flatter. So the efficiency, the 30% efficiency at high masses seem not to hold. So something is going on, but we don't fully understand how this works. So cutting the chase, what are the requirements? So we definitely need to increase the sample. So we need to study not only local star forming regions, but we need to go to map regions that are from the nearby let's say, from the local galaxy to all the way possibly to 7-8 kiloparsec from us, mapping the entire core mass function. So from 0.1, 0.2 solar masses all the way to higher masses. So what does this mean? And ALMA can do a lot, but cannot do much, because ALMA, remember that ALMA takes a very long time. It's very sensitive, but takes a long time. So, so what are, again, the requirements? So we need a probe that can be fast, that can scan fast the sky and cover large areas of the sky fast. I was talking about the Aquila Rift. We are talking about 10 degrees regions of the sky at once. What are the angular resolutions that we need? We would like to at least be able to resolve regions of 0.1 parsec, because this is the size of prestellar cores. So that means to have a resolution of at least 5-6 arcseconds at 100 micron, yeah, possibly even more. So a telescope of 2 meters, to be honest, would not be enough. Would be something a bit bigger than that. To be cold is great, because we need to be more sensitive than Herschel. Herschel was not sensitive enough. If I step back here to what Herschel did, you see that there is a note here at 0.6 solar masses that says incomplete sampling. So basically at 0.6 solar masses, the Herschel was not able to go. And we are talking about a region that was only at 260 parsec from us. And Herschel was not able to go deeper. So going cold is definitely the way to go. And in terms of wavelength range, we are talking about regions that are cold. So the ISM is roughly 17 Kelvin. So the peak is 150 micron. These regions are typically at 12, 13 Kelvin. So the peak is of the SED is at 200 micron. So if we wanted to measure masses accurately, we need to go in the Rayleigh Jeans regime. And this means to be, we need to be full in the Rayleigh Jeans regime. Otherwise, we don't measure masses accurately. So this would mean to go definitely beyond 200 micron, and ideally it would be good to go to 400 and 500 micron. So I will stop here, and that's it. Thank you.
Yeah, that's Tom Roberta. So when we were looking at CCAT, this was one of our big cases with the 350 micron imaging. My question is, why can't this be done on the ground if you had a sub-millimeter telescope? Even it seems like angular resolution wise, even a 10-meter telescope at 350 microns, the camera could do a nice job.
Yeah, so you can do this stuff. So I think from the ground, I think it's good. The problem is, again, in a way, being in space allows you to, speed is one thing, you know, you can cover lots of regions in a very short amount of time. And the ground, we know that it takes a very long time. So that's a little bit of, you know, the limitation. Another reason why from the ground, you know, you could, one of the problems is the filtering of the atmosphere, for example. That can be problematic because one of the things that Herschel provided was that, you know, you get at the same time the angular, and I'm talking about the ocular rift because it was close enough that we could resolve the course, but at the same time we could capture all the environment. So basically you are sensitive to all the angular scales. When you are from the ground, as you know, you filter because you have to filter for the atmosphere. So you have to, basically you lose sensitivity to many, to the extended emission. And that's the problem of ALMA as well. And as we know, star formation is a multi-scale process. And it's something that people, in my opinion, often overlook, that basically we really need to follow the entire trajectory from the small scales all the way down to at least, you know, ideally you would like to a few arc minutes to be able to understand all the process of the flow of masses. So yeah, these are, I think, the main two.
I was wondering about the wavelength coverage, really, is what I was kind of looking at. You need the short wavelength, so could you do it in one good band?
That's my question.
Yeah.
Yeah, I was just wondering, okay, like, yeah, I mean, how important is it to get this wavelength coverage? Like, do you do SED fitting to like pull out the structures? Can you do it with one wavelength? I mean, the ISM certainly kind of fills throughout that whole thing, but can you talk a little bit about this wavelength coverage? I mean, now I'm curious about that.
Yeah,
that's important.
Yeah.
If you're going to design something, it's important to understand,
Yeah,
you know, what wavelength we need.
Yeah,
and how essential is that?
Yes. So to go back to Herschel, you know, the Herschel had good wavelength coverage. It was great because it allowed to cover the peak of the SED. As I said, you know, for many of these objects, the peak is around 200 micron. So you go basically across with Pax and Spire. The Aquila Rift was Pax and Spire observations combined in parallel mode. So you basically had a coverage from 70 to 500 micron. And that's ideal. The problem of Herschel was that you could do this kind of studies only for very nearby objects because, as we know, Spire had a resolution of 35 arcseconds in the longer wavelengths, where basically you start not being able to resolve these objects if you go further away in the galaxy. So it's a combination of being able to cover the SED and preserving the angular resolution that allows you to resolve the structures. So it's tricky, you know, we realize it's tricky. It's a tricky business. But yeah, you have basically to cover the SED and then basically having enough angular resolution, also the longer wavelengths that basically you don't miss. Otherwise, you're killed by confusion, basically. Confusion kills you.
So two issues with the core mass function is first, the IMF is sort of integrated over the time scale of formation.
Yeah.
Of its operation. Well, the core mass function is just an instance of time. And so you need to know how long it takes each one of those cores to form a star, which could vary from core to core. And then the other issue is that the core, we don't actually know how far the core actually extends. And the reservoir of mass available could actually be larger, or, you know, it's hard to estimate sometimes just for the data by itself. Are there ways that you can approach those two issues, that the time scale overlaps and how much material is available, potentially at larger scales, to these kinds of data, particularly if you have a lot of dynamic range, your spatial impact?
I think that's where spectroscopy could help, you know, like the combination of also combining imaging and spectroscopy, because spectroscopy could help you to guide you through the basically looking at the flow of the gas in the structures, and therefore also looking at the time scales. So I agree, imaging alone is not enough. You know, imaging tells you masses, but it's not enough. So then you have to complement imaging with something else. And that's where also you need spectroscopy. In this talk, I didn't talk about spectroscopy because I think there is already a lot of, I would say, emphasis in the community about spectroscopy. I don't, you know, I thought I didn't need to put extra emphasis on the spectroscopy side, but I think that's where you need to combine the data set, because as you said, you need basically some clocks that tell you about the chemistry of what happens basically in terms of the flow of gas in yeah.
This is an interesting topic, and then saw some other hands up, but I think we can move on so that we can wrap up our lunch. Let's thank her.
It's odd.
Oh, thanks. There you go.
Okay,
Okay, can everyone hear me through the mic? Good. Okay, so my name is Benny Janssen. I'm an entropy fellow at the Jet Propulsion Laboratory. And today I want to talk to you about kinetic inductance detectors for the Terrex Intensity Mapper, or TIM, a NASA Foreign Infrared Balloon mission, and also with an outlook toward future probe missions, which have been discussed yesterday. So what you see here in the back is actually our first array for TIM. TIM is a US collaboration, many institutes, under the PI of Joaquin Vieira. For the purposes of this talk, I would like to call out two graduate students, being Rong Ni at Illinois, who did a lot of the simulation work on our absorber, Simon Liu, who did a lot of mechanical design work, and Bruce Bumble, our fabrication expert at JPL. So the scientific goal of TIM is to try and understand the 3D structure of our star-forming universe as far as it is just obscured. So it will do this by doing spectroscopic mapping, or a blind spectroscopic survey of a region of the sky, mainly trying to observe ionized carbon and ionized nitrogen lines, and do what they call line intensity mapping, so make a tomographic map of this. The survivor will also have ancillary data, namely we will probably detect around 100 carbon plus emitters, the brightest ones between redshift 0.5 and 1.7, as well as provide a wealth of data for example, stacking experiments to understand and calibrate our star formation history. So in order to do this, the Terrex Intensity Mapper will be a balloon mission based largely on the blast TNG heritage, in particular the gondola design, although this new gondola design has already some optimizations with respect to the TNG design, but also our cryostat, pointing system, and others. So we have a 2-meter mirror, which feeds 2 grading spectrometers, which together cover the 240 to 420 micron wavelength range at about a R of 250. And in order to actually see the light, each of these grading spectrometers will have a kinetic inductance detector based focal plane array of 3,600 kinetic inductance detectors. These kinetic inductance detectors will be lumped element kinetic inductance fed by a horn, which will approximately see a loading level of about 100 femtowatts, and therefore we have a detector requirement of 4 × 10⁻18 watt/Hertz. We'll operate these at 250 millikelvin, and we'll be using an RF SOC based readout, which Phil Mauskop talked about, I think, on the first day. So first hardware is coming in. Here we can see our mirror as fabricated by MTech in Germany. The completed mirror is currently on a boat and awaiting to be shipped to the US. So something which hasn't been touched on, I think, despite a few talks, is what are kinetic inductance detectors? So they are basically superconducting resonators, or resonators made out of a superconducting material. So we have an inductance here, which we couple to a capacitance, and if we read it out of this readout line, we will actually see a transmission dip at the resonance frequency. Now, as light gets absorbed here, this will break the electron pairs inside the superconductor and change the inductance, and that shifts our frequency, which we can of course measure, and that allows us to see radiation. Now, I think Jordan already gave a great spiel about why kinetic inductance detectors are so amazing. So let me just highlight one amazing point. That's our multiplexing, which means that on a single readout line, we can keep all our detectors absorbers the same, but by just giving them different capacitances, we can give them different readout frequencies, and thereby we can extrapolate this to build really large arrays. And in this case, the TIM kit array has 864 pixels, and our first measurement of this first array showed that we actually have 823 resonances, so we have a fabrication yield of 95%. So a unique new feature of these kinetic inductance detectors for TIM is our absorber design. we specifically designed this to be all aluminum, easy to fabricate. And that's also satisfied us to keep our line widths fairly large at 500 nanometers. So Wrong Knee, based on a design or on a concept by Chris McKenney, who was here at Boulder, designed this, what we call the chain link absorber. So our absorber meanders here, and on top there's these extra meanders, which help us boost the absorption efficiency in both polarizations to over 95% across our entire band. However, a key requirement for that are both the having of a back short of approximately 25 microns and strict control over this air gap between our horn feeds and our aluminum. So we need to, our goal is to have an air gap of 50 microns. And in order to achieve this, we have this mechanical design by Simon Liu, where we have our horn array. And that horn array actually, as you can see, has tiny 50 micron legs, against which we mount our detector wafer and then have pogo pins coming up from this bottom box to clamp it in place. To keep all our structure on one line, on one layer, we actually have our wafer sticking out so we can bond it into our box. So, okay, it's a bit weird. Now we have a large array, but are these detectors any good? So we expose them to our black body source, and what you can see here is actually the noise spectrum, where we have a white noise which rolls off, and while the white noise level stays the same, the roll off moves out to higher frequencies. And for kinetic inductance detectors, this is the hallmark of a photon noise limited detector, which we can furthermore confirm by looking at the absorbed power and the derived NEP, which nicely follows a root power law. So we are photon noise limited with these detectors below 100 femtowatts. If we then look at a dark detector, so which doesn't have light on it shining light on it, we again see white noise spectrum, again with a roll off, but now changing with temperature. And this is what we call generation recombination noise. So instead of photons breaking the electron pairs, it is thermal fluctuations breaking the electron pairs, which puts a fundamental limit on our detector noise and our detector NEP. And based on that, we estimate a detector NEP of 1 × 10⁻18 watt per root hertz. So we easily satisfy all the TIM requirements. We also did however you might notice, this was operation at 215 millikelvin, while TIM would operate at 250 millikelvin. So if we plot the noise equivalent power for our various thermal stages, as well as the expected NEP from our optical operation here in blue, we can see that operation at 250 millikelvin works really well. At 270 millikelvin, so if we end up with a slightly less cold cryostat, we are still good. However, unfortunately, it also demonstrated that we should be lower than 300 millikelvin, which meant we could not remove one of our thermal stages and make our instrument more easy. So we have large arrays ready, which easily satisfy the TIM requirements. So where can we go for space operation? As you may notice, our limiting NEP is 1 × 10⁻18. And as we have heard, a lot of probes need something more along the lines of 1 × 10⁻19. So in order to improve our noise equivalent power, we can do two things. We can increase our response, and our response is given by this complicated formula, which you can ignore anything in the brackets because those are material parameters we cannot really do anything about. So the two things we can do something about is we can increase the quasi-particle lifetime. So how long do these broken pairs live? And the main way of doing that is just cooling down our detectors further. As for example, shown here by Fury et al. From Jason Glenn's group, they demonstrated that for the same aluminum as we're using, just cooling it down increases the quasi-particle lifetime to a few milliseconds. And we have assumed conservatively about a millisecond of lifetime. In addition, we can decrease the volume of our absorber. So this is a new design using 250 micron lines in this cross, which reduces the volume of our absorber by a factor of 10 and thereby boosting our response. So taking that increased response in mind, we can also work on decreasing our noise. As we lower the temperature, this generation recombination noise, which I talked about, will actually also decrease. As we can see here, GR noise NEP goes down as we lower in temperature. So we expect that to become subdominant. So what I did was I took this spectrum and subtracted my fitted GR noise. It gives me this brown spectrum over here, which looks a bit ugly because of that subtraction. But if you look at sort of the top of that, that follows a nice root frequency dependence, which is a hallmark of what we call so-called two-level system noise, another limiting noise source for us. However, taking that into account in combination with the improved response, we already anticipate we are able to meet this 10-19 requirement. If we want to push even further, we could, for example, go to this design made by Peter Day, which is what you call a parallel plate design, so parallel plate capacitor, which you know from Cipro electromagnetics, and that would push our two-level system noise down, as you can see, and we would gain a factor of a few. So these are our design goals. We are currently making these devices and have fairly similar devices in measurement. First results look promising, but we need to understand a little bit more before we show them to you. But I would like to advertise the fact that there have been demonstrations that kids are indeed very ready for deployment in space by my alma mater group at Epsilon and TU Delft. So this is work done at the end of my PhD, led by Jochem Baselmans. It's called the Space Kids Project, where they basically demonstrated a large array ready for space conditions. So these detectors here, some key, these are almost 1,000 pixel array of lens coupled, in this case, kinetic inductance detectors, which show a few key highlights are that they are photon noise limited and transition into a jar noise limited regime of a few times 10-19 watt per hertz NEP, which is stable over this central section of the array. And the only reason that you don't have it on the rest of the array, as you can see, only a sub-array is eliminated, which is basically for cost reasons, because these lens arrays are fairly expensive. The other thing which is of note is that the optical performance is as designed. So these lens antennas perform as their simulations, perfectly as their simulations are. And since I had a discussion with somebody recently, these actually have a dynamic range of 10 to the 5. Another highlight of these, and that's published by Kenichi Karatsu et al., is that kinetic inductance detectors can be made fairly hard against radiation. So when a cosmic ray hits a kinetic inductance detector, you will basically see a blip. If you look at the time streams for a regular ray on a fully silicon wafer, you will see that a single cosmic ray will actually cause nearly the whole array to go off. However, there's two tricks to mitigate that. The first one being putting a superconducting material on the back, which will absorb all this extra energy and dissipate it harmlessly. And the other way is putting your resonators, or at least a sensitive bit, on a membrane, and that will isolate isolate them very strongly from these cosmic ray hits, which reduces the estimated dead time in L2 to something like below 1%. Now, a recent result, which Matt and Hannes already showed, is of course that Jochem Baselmans has recently demonstrated a 3 × 10⁻⁹ watt per hertz kinetic inductance detector, for which we see the noise spectra here, even at a lower frequency, ending up at 10⁻⁹, at an operational frequency of 1.5 terahertz, which would make them very well suited also for probe applications. And with that, I'd like to conclude. I have to show you the goals of TIM, a far infrared balloon mission doing a C+ line intensity mapping. We have the kit arrays that are ready for it and satisfy all the noise requirements, and we are working on improving our NEP for probe deployment.
So how short a wavelength can you go?
How short a wavelength can you go?
Yeah, well, okay, so we creating something for 10 to 240 to 420, but the far infrared probes are talking about 25 to 500, or, you know, we don't know yet. but-
Yeah. So the aluminum and the detector design can be adjusted. I think the main challenge, which has been always a challenge with kinetic conductance detectors, is making sure your optical coupling stays good. And that horns, of course, become extremely small. Lens antenna coupling is a lot better. And for example, the latest results from Jochen Baselmans, they have an iteration which already operates at 8 terahertz of that antenna. So there are definitely options, and we're working.
I was just gonna add right here and propose that this low frequency noise that we see is not fundamental to the absorption. We haven't worked hard to mitigate that. We haven't needed to. Now we're starting to really get serious about the probe. So I expect we can improve that and be open to indicate the same kinds of things that is for level system.
Yeah.
There are ways to do that.
Oh, yeah. So I know with the large format arrays, one of the concerns is uniformity. So I was wondering if you can make a statement about the uniformity and performance, not taking into account the illumination, the change in illumination across the array kit. And I was also curious about crosstalk.
Yeah, so for the large array, we are now in the process of actually going from simple these things work to actually measuring them in detail. So in terms of array uniformity, can I say something about that? So at least all the coupling queue and the internal queue, which we expect are in line with what we expect, and their spread is not much higher than our small test arrays, which is a factor of a few. Similarly, for their thermal performance is completely in line with their thing. But we need to, especially optical performance, we need to test in detail how uniform the arrays are. In terms of crosstalk, we tried to do magnetic shielding measurements, and as a result, we had a lot of crosstalk or a lot of collisions in our resonators. So we're hoping to do a more stable measurement with magnetic shielding in place. But first measurements of trying to null our magnetic field indicates that we have about 100 collisions, which we need to correct for using trimming methods pioneered here at NIST.
Moving away from the arrays, looking at individual detectors. How accurately can the arrival of a photon at a detector can be timed? Is that a possibility?
That is a possibility if we were to make these even more sensitive. So at this moment, for these wavelengths, we are not in a regime where we can actually do photon counting. For that, we are too slow. But there are groups, Ben Mazin being the most prominent here in the US, and Peter de Visser at Esron, working on optical and near-infrared kits who can do photon counting.
Hi, great talk. Thank you for it. I believe you said you have an air gap of around 50 microns designed between the waveguide block and the detectors.
Yeah, that's correct.
That's nearly a quarter wave at your shortest wavelength. So I've seen problems with leakage into that gap and more coupling issues when you get that large relative to wavelength. My personal rule of thumb is at least it's got to be a factor 10 smaller than the wavelength. Have you looked at closely the leakage into that gap and how might it affect your coupling along?
So we have, at least wrong in simulations, has looked very closely at that leakage. So what we see here is power leakage, and now I lost too much. Okay. One of these is power leakage through the gap, and I would expect it's this one. So what we actually see, and that's more or less why we decided on that 50 micron air gap, is that as we go over that 50 microns, our air leakage through the air gap to other pixels is dramatically increasing. And that is one of the primary reasons why at that moment also the absorption efficiency starts dropping. So that has been on purpose a decision there. The other reason, and that was a bit pushed back from the fabrication aspect, is that there have been, I think, issues with blast where the 50, like anything smaller than the 50 micron air gap started breaking wafers. We have a bit more flexible setup, so we could probably go smaller. But I appreciate your comment, and I think we'll have to, especially the quarter wavelength, it might be worth revisiting.
Okay, let's thank them again. Okay, before we let you go for lunch, I know that a bunch of you are going to disappear because you're catching flights to places, and that's good and natural, and we were hoping this workshop would be drop in, drop out. But I would like to take the opportunity to thank sincerely the organizing committee. So Roberta, Stacy, Ariel, wherever she went, Kevin, Jens, great job, and most especially Meredith and Jake, who have busted their backs trying to get this all together, and you see them running around, and it's been a lot of work behind the scenes. And we should all really appreciate the comments. So we'll break for lunch, and we'll pick it up at 1:30. We have a couple thoughts, and then we're gonna kind of try to wrap things up and figure out what the next steps are. Thanks.
Did you think quasi-particle heating is going to be a problem as you go to more and more sensitive detectors? Because your readout, I don't know, like, are you TLS limited?
So the reason we're more conservative than the 2.5 microseconds that's previously demonstrated, because that cap in lifetime is known to be readout heating, basically. That's one reason
Okay, everybody, we're going to start up again. Terminal session.
All right. I'll give you a second to take your seats. All right. Well, I am pleased to welcome our next speaker this evening, Ms. Boulder, who will be talking about superconducting analyzers and superconducting detectors for
All right, well, I'd like to thank the organizers for giving me the opportunity to speak today, and everyone who's here for deciding to come listen to this speak in the workshop. So it's going to be slightly different than a lot of the other talks. I'm going to be talking today about a detector technology that, for this community, the mid-infrared and far infrared, nobody uses this technology. But in the near infrared and optical, it's an extremely popular technology in basic science and quantum information, quantum computing, as it's one of the most, probably the highest performing single photon detector in those regimes in terms of efficiency, speed, background count rate. All those things are really very good in the near infrared optical UV, and we are starting to explore how well we can do it with IR and maybe even into the far. So let me just tell you where we are, how the detector works, where we are in terms of making arrays, and then if you're interested in working together, just contact me. All right, so and this is a picture of a okay, it's all right. If I stay on the stage, it goes away. Stay close to. All right, is that better? Should I switch to a handheld microphone?
Maybe something's on here.
Okay.
That's
Better? All right. So the background of this title slide is an example of a small, I think this is probably either kilopixel or 10 kilopixel array in the near infrared. And this is a lot of the work I'll talk about today has been done at NIST and jointly with JPL and MIT. But I don't think any of the results here we'll see are from joint work with MIT. So these are the people who have been involved, who are involved and who may have been involved recently. This is the group at NIST. This is, I think, most of the group at JPL. I'm sure I've forgotten some names there. And then I should acknowledge that a lot of the work that has gone previously has really been supported by DARPA, NASA, and some internal money at NIST. So I'm going to go through how these detectors work, since most of you may not know. I'll compare it to a very crude table, and it's not complete, and I'm sure I may offend people who work on some current technologies, but I apologize in advance for that. But just to give you a sense of where it sits relative to other technologies. And then stuff that we've been trying to do to get it to work in the mid-infrared and longer ranges. Whoops, and then talk about arrays. All right, so this is probably, what I would say, this is probably the simplest thing you can think about trying to do with a superconductor to make a detector. And that is to bias it with some current, all right? And then hope that when a photon lands, you break the superconductivity, disrupt the flow of current, and then detect that disruption of flow and current as you're seeing. And for us, I think this was pioneered at Moscow State Pedagogical University back in the late 90s. And typically they were making very narrow
So on the order of 100 nanometer wide wires or strips, and very thin superconductors, 5 nanometers. So most conventional superconductors, they don't superconduct when they're that thick. So you have to find good superconductors that will work at this thickness, so that when a photon is absorbed, you can break the superconductivity. And one of the issues when you have something with this kind of dimension is that, it's say a 1 micron photon. The odds of your 1 micron photon getting absorbed in that tiny little strip is very low. So you need to figure out a way to pattern it into a meander that's much bigger, that's bigger than the single photon you want to detect. And this is typically what we make when we're trying to make, this is a SDM picture of a detector we would make to detect, let's say, 1.5 micron photons coming out of the end of an optical fiber. So the line widths can be anywhere from 80 to 200 nanometers, and it just lines back and forth to try to capture as much of the optical mode as possible. So let me go through how this works. I kind of gave the punchline away. Yes, you have current flowing through your device. You hope that when a photon's incident, you create some kind of hotspot, and that the hotspot spreads enough that it breaks the superconductivity along the wire. There may be a belt of material that no longer superconducts, and since it no longer superconducts, if you've embedded this wire in the right kind of electronic circuit, the current that was flowing through the device can get, let's say, redirected to your amplifier. And what's great about this kind of device is the current can be pretty big, and the amplifiers you need cost about 5 cents or 10 cents. I mean, they're the kind of things that run our cell phones. Those kinds of amplifiers can easily beat out the signals coming from this kind of detector. And so you can get a pulse. In this case, the gain in the circuit was negative, so we see a negative pulse in this case from the oscilloscope capture when it's detected a single photon. And my group has been doing a lot of work at optimizing this to the near infrared, 1.5 microns, maybe up to 1.8 microns. And we've been recently trying to push this into the mid-infrared. So this is how the detector works. It's pretty simple. One of the nice things or amazing things I would say is that when we have large area devices like I showed, which was the 15 micron diameter device, our jitter can be as low as maybe 50 picoseconds. So the identification of the timing of when the photon arrives in the picosecond range. And if you really work hard at engineering, we have a paper where you can get the timing jitter as low as 50 picoseconds in terms of uncertainty in the photon arrival time. The larger detectors, after they see a single photon pulse, they tend to decay on the order of tens of nanoseconds, maybe 20 nanoseconds. But again, with an optimized device, you can push that down to a few nanoseconds. And I think what's great is that it's just a metal, just like we hear about MKIDs and TPSs, they can absorb electromagnetic radiation. This can absorb anything that a metal will absorb. And I think one of the most recent extraordinary things that we've done in the last couple of years is that we've shown if you properly shield against background light, the dark count rate, the false click rate, the probability that the detector will fire, even though there was no photon, is less than a count per day. And we believe really that's due to right now cosmic ray muons or background radiation in our device that we haven't shielded properly from. And we believe the intrinsic background or dark count rate is going to be much lower than a count per day. I don't know how much lower we will do experiments to figure it out, but we definitely have data. If it hasn't been published, it'll be published soon. Where we're less than one false click per day. And so those of you who know or are good at calculating NEP would quickly realize that this is, say 1.5 microns. This kind of NEP is 10 to the minus 22 or something. If you say you get this kind of count rate at 100 microns, it's 10 to the minus 24 watts per liter. But yeah, so that's pretty exciting. That intrinsically the dark count rate is extremely small, and I think that means you have a lot of interesting applications where you're looking at ultra low faint sources of light, or in high energy physics, ultra rare event sources. Oh, okay. So here's the table. I tried to summarize some things. One of the nice things is that we can get nearly 100% detection efficiency. Sorry, this is the detection efficiency by using like optical coatings and things like that in the near infrared. We don't know how well we can do in the mid infrared just because we're not sure how compatible the materials of the mid-infrared, maybe far infrared are with the superconducting materials that we're using. I see that the internal quantum efficiency is nearly 100%. That has not been proven by anyone, but most of the experts in the field believe it's pretty high. And that's a difficult experiment to try to determine. And then this is me translating this 1 count per day into some kinds of NEPs that one could achieve. So this is already done today, this kind of ultra low NEP at 1.5 microns, and it's being used today to do dark matter searches in high-physics experiments because of the ultra low false clip rate. And right now, we typically try to run about a 1 Kelvin operating temperature, it's just easier to have a 1 Kelvin refrigerator than a downstream refrigerator. And the materials are just running that temperature. But in the future, we really want to try to push out towards 100 microns. We probably have to go towards a downstream refrigerator temperature. But I don't really know, that's very speculative. And it's the kind of research we'd like to do to see if this technology could be used for far infrared. All right, so a lot of the work that's been important in the quantum information computing community using photons is really trying to get the detection efficiency as close to 100% as possible. There were a lot of papers in the early 2000s that basically said if you didn't have 99.99% efficiency in detecting a photon, you couldn't do linear optical quantum computing. The threshold has now changed, and now you don't need 99.99%, but it's still very high. So a lot of the work that my group's been doing is trying to get that ultimate system detection efficiency as close to 100% as possible. The obvious thing where the efficiency could be bad is that you can't couple the light. Everyone understands this problem, especially astronomers and astrophysicists. Another thing that can happen is the light may get reflected. I'm really bad at these clickers because my fingers are not very coordinated. And they're not that fat, but anyway, I'm just uncoordinated. All right, so one thing that you need to make sure happens is that your metal absorbs the photon, and then and that's the absorption, let's say, that leads into detection efficiency. And if it's absorbed, not every absorption event generates an electrical signal that you can then detect, and that's the internal quantum efficiency, or what I call internal efficiency. And we believe this is 100% for our detectors, but it hasn't been proven by anyone yet. So we do a lot of things to make these things close to 100%, and I'll go through some of that. One of the big things that we did was the conventional material being used and, let's say, invented by the Russians was the use of nitrogen nitride or nitrogen nitride. Well, these nitride superconductors are really fantastic materials. They have amazing properties. And you can get really good single photon detection with well fabricated nitrogen nitride. But it turns out not everyone can make high quality nitrogen nitride. It's very tricky. And what people have found, it's very tricky to make that high quality nitride to cover any large area of a wafer that you might want to do to make an array. One of the things that my group has figured out was that let's try to use an amorphous material instead of a polycrystalline material. So they don't depend on the substrate for to get the right crystallinity to make a high quality detector. If it's amorphous, you deposit it anymore. So we pioneered the use of these amorphous superconductors. They have a lower TC, a lower carrier density. It just means in the end that the hot spot that we may get is bigger when a photon's absorbed. So that makes it easier to detect a photon. So higher internal efficiency. The other thing that is less obvious is that we get much higher yield and less distilled potentially arrays of detectors. The drawback, though, is that these amorphous materials don't have a TC. The nice thing about nitrogen nitride is the TCs in the thin film forms 9 kelvins, and refrigeration is trivial in comparison to a dilution refrigerator. But this disadvantage of this amorphous superconductor is the TC is on the order of 3 to 5 kelvins. So you need a slightly better cryo cooler if you want to be cryogen free than what you need for nitrogen nitride. The other thing we can do is we can also tune the amount of tungsten versus silicon in the material. So tuning the alloy that we make also affects the TC and the performance of the device. And what we have found trying to go to a mid-infrared is that if we tune it so it's less metallic, we get better response in the mid-infrared. And so this is an example. So this you'll see these kinds of curves with these kinds of detectors. This is a very classic curve that people show, and this is the current that's being used to bias the device, and the y-axis. The y-axis is the count rate or some normalized count rate or efficiency, and the blue is an example of the count rate or normalized count rate that we see when we illuminate this particular device with 4.8 micron light. And what you want to see is this nice long plateau. And what that means is that if there's any noise in your bias or electrical pickup, the efficiency isn't changing. The probability of seeing a photon is constant. And that's a signature of a good device, for that color. And as you can see, as you go to longer colors or less energy, the probability of seeing it click isn't as high at the same bias point. And that's because there's less energy, your hotspot maybe is a little smaller, and the probability of click is reduced. So if you really want to see good detection, let's say 10 microns, you'd like to see this red curve to be more like the blue curve, flat plateau. But there's still hints that it has plateaued, which is a good sign in terms of trying to get good single photon detection in the infrared. Okay, and then one thing that you'll often also see is dark counts plotted in black, and that's there's this axis for the dark counts are on a log scale now. These are the dark counts, and what ends up happening is this often follows some kind of exponential. So if you want to detect 4.5 microns with low dark counts, you want to bias lower in current, so the probability of a thermal fluctuation in the wire causing a click goes down exponentially as you go away from the maximum current bias. So a really good, single 1 count per second may not be in this saturated efficiency, maybe over here or something, but that's because there's this exponential fall off. So the better or higher quality device, the longer this plateau is, and the further away you can be your bias from the very edge, where it'll be more noisy. All right, and then just like everybody else we heard this morning, you embed your structure in some kind of optical stack to enhance the efficiency. We can do the same thing. We can control the bandwidth over which we can detect efficiently. And then here's a picture of our setup. I don't know, the optical rays disappear out of this spectrometer, but we have a cold cryogenic monochromator at 40 Kelvin that we've coupled with the integrating sphere and some optical fibers, so we can try to fiber couple and test. For the mid-IR, our detectors at 300 millikelvin and compare it to a reference bid detector at 4 Kelvin. So here's our 40 Kelvin monochromator and our refrigerator. This is approximately, this plate here is approximately 200 millimeters across. So it's a pretty small refrigerator we've got running with our cold monochromator and our detectors down to the helium 3 stage. That's a test setup. So let me show you some examples of some detectors we've been doing. So one of the interesting things that we've done is we've been trying to do the simplest kind of multiplex readout you can imagine. So that would be like if I have n squared pixels, I have n readout lines for the row and n readout lines for the column. But there are lots of multiplexing ideas out there that you'll see in the literature. And one of the interesting things that we've done in the mid-infrared is that when we have basically a bunch of wires that are maybe form a row with red lines, and then we have detectors that form like a column. And this is kind of a trick, I would say, that we can do. When a detector fires, let's say the red detector fires, locally, it gets hot, but the current that was in the device actually will dump a little bit of joule heating because there's energy stored in the inductance of the device. In undergraduate E&M, you learned that the energy stored in inductors one half Y squared. The inductance actually has the inductance of this device is very large. It actually has a lot of energy on the order of keV of energy stored in the device when it's superconductive. And once it becomes resistive, that keV of energy has to dissipate in the hotspot. So if the red detector fires, you get about a keV of energy deposited in addition to the photon energy. And if you have another nanowire close by, it can get hot and break its superconductivity. So in this case, we're doing a trick where if the red one fires, it also causes the blue one to fire. So we have these kinds of amplifiers, the blue reading out column, and we have these red detectors being rows that are being read out that way. So if the detector fires, you look at which row and column amplifier gets a signal, and then you can figure out which gets the fire. So that's a very crude way to do multiplex readout. There are more sophisticated ways out there, but this is easy for us to do. No phase lithography, it's all one layer. It's just an example of what you can do with these kinds of devices. And then we've been making arrays. This is I think an 8x8 array, and we had a yield of 60 out of 64, which is a little unusual in terms of how low the yield was. And this is the light curve, the photon count rate as a function of bias, 3.5 microns. This is pretty typical for a pixel in this array. And then we're in the middle of trying to test a kilopixel array, and ideas on getting to 10,000, things like that. So let me, maybe I'll just end there. I think going into this workshop, I didn't know very much about exoplanet spectroscopy. I still know nothing really, other than reading the different reports. We think it's a pretty interesting device because I think we believe we can work from 1 to 20 microns without a problem with ultra stable gain and ultra low dark counts. But we don't know if it's really a good instrument. We'd love to talk to people about whether it could be used in such an instrument. We've done some terrestrial experiments to look at differential absorption LiDAR signals for greenhouse gases, so kind of the biosignature-like things you'd be looking for, but on the ground here on the Earth. And we've taken data and compared it to TMT data, which is the standard thing used today. Let me just end here that we're excited about the possibilities of this kind of detector, and would love to talk to people about whether they thought it could be used in their kinds of instruments and for future missions. Thank you. Any questions?
So what's the dynamic range of the detector? Because I mean, it is true that I don't think we have too many detectors going out in this wavelength range there to produce it. So having other options is a good idea. But what's the dynamic range that you can?
So that's a good question. So I don't know what the limit is. Like right now, if you just hook it up to hook up a detector to a counter, you can count per day up to million counts per second. But certainly the JPL team has done a million counts per second detector systems. A single pixel, 10 million counts per second isn't crazy. So I don't know what your low limit is for defining the dynamic range. 100 million counts per second probably would be something you would do pretty straightforward ways. And then there are clever ways of averaging that maybe let you do about 100 million counts per second. It wouldn't be the same in terms of counting every click. Maybe you just integrate it with count counts per second to be average count rates, and that could be done at higher for higher count rates. But that, I don't know what the limit is. So.
Any other questions? From what you just said, your dynamic range is more than 100 dB.
Yes.
No, it's like 150 dB or something like that. 150 and 30 dB.
Well,
enormous.
Yes, but you got to remember that it's normalized to something close to 0, right? Any number divided by 0.
Right. So, yeah. So okay. I have. Is there a potential mixing application with this kind of device? I'm just curious.
Yes, you could use this in a mixer style thing. Whenever I've looked at that, I don't think it's a good idea.
Okay.
But maybe it depends on your system, right? It's possible. Yes, you could use it in a mixer. Yes.
You said that we can determine the photon counting, the timing of photons per picosecond. These devices are very fast, right?
Right.
That's like a terahertz.
Right.
So given that they are that fast, if there is some nonlinearity, then it's pretty
I mean, I have always thought, oh, it's got extraordinarily good timing, uncertainty, very low jitter. But in most astronomy applications or astrophysics applications, no one needs timing at that level. So you want to trade that exquisite timing for something else, whether it's the multiplex or, you know, it could be mixing. I don't know. But most of the time, that's overkill for a lot of the applications that we've heard about today. You don't need 3 picosecond time.
Okay, I have a question for you. A couple questions, actually. Have you looked at granular aluminum for this, since it has a high inductance and non-IR related? Have you looked at this in applications for time resolved, like electron emission tomography?
Okay, so granular aluminum, yes, that's a very interesting material. Since I've been mostly focused on optical and near infrared, I usually think making a detector out of aluminum is a bad idea. And mainly because it reflects most of the light. But that's my personal opinion. You don't want to make a detector out of mirror, but there are people who I'm sure will go do that and write PCBs and things like that. But it could work, yes. I agree. It's an interesting idea. Yeah, head tomography and things like that. I agree. Those are things we'd love to work with people on. We just haven't found the right people yet to do that.
Other questions from Sadie?
Would it be possible to put them on membranes if you had to go there for the space?
Sure, no problem. We do that now. So the mid-eye infrared, some of the better results in terms of getting to longer wavelengths is to put our devices on membranes. That way the heat may be trapped there locally by the wire and not disappear into the substrate.
All right, let's thank Sadie again.
This will bring it up.
So it works. Did I do that? Yes.
Yes.
Fantastic. Okay, our next speaker is Gordon Stacy. Now, talking about silicon substrate based spectrometers.
Okay, thanks very much. I want to thank people, the organizers, for enabling me to come and shop my wares a little bit. Thank them for the whiskey thing last night. Thank the whiskey place for also having gin. Thank the bus driver for leaving at 9 so I don't have a headache. Yes, sir? Oh. Most people prefer that. Okay. Good, now the classes won't fog up. So anyway, let me get to the talk. Talking about some stuff we've been doing the last couple of years at Cornell. We're developing a silicon substrate based out of probe mirrors. And we envisioned that they could be used for 25 microns the way out in the millimeter regime by varying parameters. We long heritage, a tour through that in the doing far infrared the sub-millimeter wave band fabric probe spectroscopy. We improve with the silicon substrates the technology we used before, which was this simple metal mesh technology in both bandwidth, transmission, surface quality, and robustness. And so we think they might be a very good choice to achieve moderate resolution in the infrared probe missions. And here are the cast of characters, senior scientists, Thomas Nicola is involved in everything I've done for the last 20 years. Kayla Rossi, the engineer, graduate students, Nick Cothard is now a postdoc at Jason Glenn, Bagao Zhao, Jackie Lenevsky, undergraduates, a couple pictures of them as well, Kenny Vetter, Mihiro Abbey, and Ellen Lee. And some quick science examples to motivate us. The large format 2D arrays, if you have those, fabric probes are a good way, obviously, to get spectra because you can do spectroscopic imaging. And if you have a single line, you can argue that they're the best use of an array of detectors. You could do things like image the galactic center. This is obviously an image of the galactic center, both with 30 micron and 12 micron. and do the spectral lines to get the physics of the regions of the galactic center. And you need high quality control and small sizes to make the fabric pros that work at that sort of wavelength. So we haven't gone there yet. We've been doing the easier stuff, longer wavelengths. You can image nearby galaxies like M83 in the far infrared fine structure lines, and do it in a very wide field of view. So for instance, here's the PPLS field of view, and there's what the more or less maximal wide field fabric pro would be on M83. Large bandwidth requirements, because you don't want to change your fabric route as you change from one wavelength to another. So that's one of the things we're calling for. Also protostars and protoplanetary systems. Hermes was designed to do that. It employed 8 cryogenic standard fabric probes that worked from 25 microns to 122 microns. 3 generations, low, medium, high resolving power, required 3 different bands because of the limited bandwidth of the metal mesh fabric probes. And you can do, of course, the science we've heard about here several times, molecular hydrogen, water, HD, oxygen, tomography, to find out where they lie in the disk. And for that science, we need resolving power of about 10 to the 5. And I already said that. And you want to do it most efficiently, a uniform or gently rising as the wavelength finesse to improve the performance of the fabric probes. And finally, the last thing I just throw in quickly, we're doing line intensity mapping with fabric probes in the millimeter regime. And when you do this C+ line that redshifts between cosmic cosmic noon and reionization, you pick out the astrophysical structures from the underlying dark matter, and also watch the process of reionization. And that machine needs good finesse over a factor of 2 in bandwidth. So fabric probes are resonant cavities. That's all the way I've thought about it ever since I worked with Charlie Townsend, the laser guy. He's a cavity man. And so it's resonance cavities, and that's the easy way to think about how things are going. And so you have these fringes, they're spaced equally in frequency space. And it does work. And so there's the various fringes of a high order fabric probe. We use, for example, a lower order fabric probe to pick the fringe of interest, a low pass filter to separate out if you have 2 fringes there. And the things you have to worry about are performance limitants include ohmic losses, because every time a photon hits the mirror, it has a chance of being absorbed. The finesse is the equivalent number. It's the quality factor of the resonator, or the equivalent the number of ounces of the photon in the cavity. You would like to have a finesse of the order of 50 to minimize the losses. Typical losses are 0.5%. You start getting to 100, you get more serious losses. You have issues with the surface roughness. You have to keep these things smooth, and that's effectively a ruse factor we're talking about there. You have issues with the flatness of the etalon, or the tip of the etalon, which you could think of as a figure of the mirror sort of things, and the aperture effects as well, and then with the resolving power to divergent beams. So we have a long history of metal mesh fabric probes, starting from the olden days before the invention of cameras. So I couldn't find any pictures of my adventures as a postdoc. But then I got into the next generation fabric probe on KAO with here's Townsend Gensel, undoubtedly looking at the galactic center and using a very sophisticated method of locating things on the sky, very precisely drawn with a German ruler. And this is a DP fabric probe, mission fabric probe. And then we built, when I went to Cornell, we built a fabric probe for shorter wavelength work. They have bibs in the background, and this is sort of the general architecture of all the fabric probes that we've used in recent years. And there's an image of the galactic center again at 38 microns. And then this brings in a graduate student. I don't know where he went, but he was pretty good and worked with me. And he made this instrument called Spiffy, South Pole emission fabric probe for interferometer, worked in from 200 microns to 350 microns, and we did some work there at the JCMT in the Galactic Center. Same sort of style of fabric probe, just a lot bigger. And there's some young people with their instrument in the basement of JCMT. That thing was taken to the South Pole, And so it went from the world's largest submarine telescope to the world's smallest, the Astro telescope at the South Pole. And we did some cool stuff detecting measuring two from the ground. And the nice little map popped out, and we had some fun too. And the most recent work that's done is the work we did with the tunable fabric probes for Hermes. There's just a demonstration that we get a resolving power of 100,000 fabric probes. And we built a series of 8 fabric probes. Here's one of the high-res fabric probes. They get resolving powers up to 100,000. Mid-res to sort the orders, and low-res that we actually use for imaging spectroscopy, we were planning to. Here is a close-up of the low-res fabric probe that we're actually thinking we could modify for use in the probe missions. We had 2 versions of that, both the short and long wavelength versions of the imaging spectroscopy. Those fabric probes are all made and delivered to Goddard. They were mounted on the wheels and tested out, things like that, but that's another story. So these are all freestanding metal mesh fabric probes, and they have their limits. They use commercially available mesh, can only buy certain sizes, and it was all inductive mesh, which means it looks like a window screen. And that mesh has characteristic reflective properties. That means the finesse is a strong function of wavelength. So the resolving power at a given spacing is a strong function of wavelength, which isn't too desirable. Those is lambda squared. And high finesse can be crippling to that long transmission due to absorbance. The bandwidth was limited for the same reason. You didn't want to get the finesse too high. You get it too low, you get leakage to other spectral orders. And there were structural issues with those things. They're delicate. And also there was roughness issues. The layers of metal were rough. So we moved to silicon technology where we can control the structures, the reflecting structures. And you can make either inductive or capacitive structures or combos thereof to try to maximize your efficiency and keep the reflective parameters uniform. The surface is extremely smooth, and we can make them with 0.5 millimeter thick substrates that are very high purity silicon and very flat. The bonus is you can also put on superconductors. We haven't tried that yet. And the negative is this index of refraction. And so that was the thing that we struggled with for a bit, but we managed to do it. So we're using metamaterial structures. You can either make pure, let's say waffles or waffle irons. And we voted for waffle irons because the walls have structural integrity and we have thin things. So that's what we were making. You can get very good transmission in narrow bands with a single layer. We do broad bands with one with a double layer. And so that took more learning curve time. In the end, we got a good performance, and I'll show you a bit later. I want to emphasize we're going to focus on 100 microns and 1 millimeter. That's what we've done our development with so far. The 100 microns was very relevant for things like Hermes. The 1 millimeter is the ground-based spectroscopy, the IR STIG. But you also, this is very obvious, 100 micron for things like both the Prima and First. So there's our double layer AR structures, millimeters, one this one, the 100 micron one there. You can see we have very nice structures, and they're predicted to have a very good transmission, and we measured the transmissions of the curves in single things in the imaginal model, so that's very reassuring. And then we went through the modeling of metal surfaces. We tried, I think, everything, and we tried the obvious things that come to your brain, making crosses, making combos, and making all sorts of stuff. But it was very frustrating, and we ended up with not any real improvements. And then we had the onsets. Why not make one of the 2 mirrors, a inductor and the other one a capacitor? And that worked pretty well. It does work pretty well. We made these and tested them. So one has this sort of grid, the other has this sort of grid. You put them together, and you get the combo giving you a reasonable finesse. You can see the finesse is as low as 30, but that's the bounce. Low as 30 and high as 60. So that's not bad over a bandwidth of a factor of 2 frequency. And the transmissions 60% and higher. So it's not bad. And this is a model at millimeter. Model at 10 times the frequency is essentially the same, and we managed to make both of those. this is on a 525 micron silicon substrate. Relevant to this next slide, a better solution. So we made these, and then after some more thought and use of CST, Zhao discovered that if you brought the substrate metamaterial very close to the reflector, you could tune the metamaterial in the reflector and get rid of a lot of the problems with the envelope of the AR approach, and get much higher transmission and much and broader bandwidth. And so this is over a bandwidth from 2 terahertz to 4 terahertz. He gets finesses that are pretty flat from 60 to 40, and they actually go up in the direction you want them to go up as long wavelength. And so that will give you sort of a uniform resolving power of 5,000. But of course, when it's a wavelength thick, that's not very thick. You know, it's 100 microns, 50 microns. It's pretty flimsy stuff. So we're not really happy with that. We're sort of happy. But then some more thought, and he discovered that if he learns how to run CST much better, I think this must have been pretty hard, and was able to change the pitches on both sides of the etalon of the structures. He was able to get something that looked good all around. And so this is the transmission envelope. Now it goes from 92% to 99%. This does not include the ionic losses, so you got to put a 10% or so on top of this, but that's pretty amazing, right? And so we're excited about that. We haven't made it yet, but we're excited about that. And the bad news is he's got an issue with the finesse, and so he's working on that. But we're encouraged that we're going to get a really nice thing. And these are normal size substrates, 0.5 millimeter. So we haven't done as much testing as I'd like. I had issues with our test devices, but I'm just going to show you one quick thing that ensures me that we're doing something that's reasonable. Here's predictions of the inductive capacitive mesh at terahertz frequencies. The transmission is a function of wavelength of temperature at various frequencies. And here's a measurement. It looks a lot worse. The measurements are the harmonic lines here. These are garbage lines from the atmosphere and the FTS. And so you think, oh gosh, it's very disappointing. But then our resolving power of FTS is significantly smaller than the fringe. And so therefore, we have to go back and convolve the prediction with the FTS sync function, and you end up with predictions that are these blue things. And so we're actually pretty close to what the predictions are. Clearly, we're going to make more measurements with a higher resolution instrument, and our plan is to use one of our heritage traffic pros. And so the applications to the probe missions, you want article 10,000, for example, Prima, that ballpark, say it covers 70 to 140 microns. You insert the Fabric Pro into the beam, calculate at 25 millimeters to get the sufficient resolving power. Illuminate as much as the long slit as you can, and still get your optical qualities. Choose a resolving power. That the order, if the finesse is 50, is 200. So the Fabric Pro will resonate at one wavelength, and other wavelengths will be separated by 0.5%, 1 part 200 of the fringes. So you have all these fringes going along. You put your pixels down there in the dispersion direction to hit the fringes, and you scan. And so you get the whole octave of light coming through when you scan the free spectral range, which is 50 resolution levels, an estimate of resolution levels. This is the Hermes device. This is the imaging device. It's a small little guy. It weighs like less than a pound. And these are the metal mesh rings with the right. This whole thing is the right size for this 100 micron work with the probe mesh. We use a flexible parallelogram. You can just push on the box, and it translates parallel for small amounts. That works just like almost all of every processor with that method, so we know how that works. We use as actuators either PCTs or cryo stepper modes. We're now baselining. We were told this, we had to build one tomorrow. We built this one, which is stepper motors, little cryo stepper motors. They have capacitors to ensure that we know where we are. Here's a quick and dirty sketch. Take out the mirrors. because now we're gonna use nickel on the back of the piece of silicon and magnetically attach it to our walls. Get rid of those mirrors. They weigh a bit and then it makes a bigger cavity and suddenly you're done essentially. And so just as a note, this guy could translate almost a millimeter with hardly anything referred to, so you could actually change resolving power at some point too, as well. So conclusions, same as they were when I started. I was amazed. Developing mirrors with heavy program parameters, long heritage, improving the performance, and I think they're a reasonable choice for a prohibition. Thank you.
Take questions.
I don't know if you're offering a course in this, but I'd like to sign up. I can see why finesse of 100 is bad. I can see why finesse of 1 is bad. It's not clear to me why 50, maybe you could explain why 50 is optimal. Is it soft or?
It's soft, it's soft. If you have 30 and it's beautiful, it's great. If you have 60 and it's beautiful, that's great. If you have 15, there's too much crap between the orders. Yeah.
For the metamaterial reflectors, have you tried unit cells that are not just like simple one-fold things, like traditional crosses or squares that are like inductively coupled? Because that might give you the flatness that you want.
Yeah, we did do, we spent a lot of energy in the early days of this project. I think I showed crosses and squares. Those are a couple, that's what you're talking about.
Well, here's your possible.
So I'd say
More capacitive coupling at the edge of the pixel.
more capacity coupling at the edge of the unit cell.
Yeah.
Yeah, I think we tried that too. I wish one of the students were, because they tried many things. And we were getting pretty frustrated. Thinking we were going to solve this problem.
Jordan.
Yes, you told us that it works better when it's close to the AR, is it a quarter wave, a half wave, one wave?
It's more like a halfway.
Halfway,
Yeah.
okay.
Yeah, I said one way, but it's a
Some
little bit.
interaction with the residual reflection.
Yeah, that's exactly what it is. He's playing around and getting the interaction to kill off the losses.
Yeah, very cool.
Yeah, I was astounded that it worked that way, but yeah, he had to convince me, but it worked.
Any questions?
That was it. Margaret.
So what flexibility do you have in terms of like how big and how small you can make this? Because you talked about putting this on a space mission, but there's always massive volume there.
Yeah, the little guy, you know, Thomas did about, I don't know, 4 hours of homework, which is like, 2% of his day, to get that far. And it's about it's about a pound. And you're gonna scale, if you want to scale it, so it's like a small, 30 millimeters or something. And if you were to scale it, the biggest ones we're planning are 15 centimeters for the EOR spec. But it's really up to what boundary you find. At Cornell, we can barely make that. There's people commercial places that can make it bigger. So we can make it bigger. There's no compelling reason that we couldn't. And then the mass would go up, of course. I expect it's not gonna come anywhere close to going as R cubed, more like R squared, because you're just stretching the square. Sorry, so much. I put some more reinforcement preventing.
Other questions? So is your bandwidth limited by your AR code? And if so, could you, like, your 2-layer, could you choose something with a bigger ripple, and a wider band?
Yeah, if we went to 3-layer, we could get a bigger bandwidth. It's one to answer that question. Yeah, that's for sure.
I don't think.
I really don't come go home with it. Okay, our next speaker is Imran Mehdi from Caltech GPL and also from by Martina White.
All right, thank you. This is, I guess, the terminal talk of the terminal session. And thank you to the organizers for organizing this. Give me a job well done. So what I'm going to do is talk about heterodyne technology or high spectral resolution technology. And it's really myself and Martina Winkler from the Paris Observatory. We put these slides together, and certainly a lot of this credit goes to people around the world who've actually being able to keep pushing the technology forward. This is just a very quick outline. The first part I'm going to go through really fast because that's essentially what this workshop has been about. And I just want to give a quick status or a quick mention of these three currently in production or working observatory, and then talk about really most of the talk on the technology thrust that we've been able to do in the last 2 years, and how we now think that we're really at the point where we can feed 64 to 100 pixel array at the Earth range. Okay, so it all starts from the origin STDT, and just very quickly, I think it's the big three science cases to make, and I think there's general acknowledgement that to get the gas excitations and kinematics, you really need a high resolution spectroscopy. Another slide I took from origins, and again, it's not, for me, it's not really a direct detector versus heterodyne. It's a tool in your toolkit, and depending on the size. So if you really want very, very high spectral resolution, then heterodyne technology is the way to go. And obviously for the sensitivity, the direct detector technology seems to be the ideal. And as part of that STDT, when we looked at the heterodyne concept, which was called Hero, we identified a couple of things that we really, as a community, needed to concentrate on to really bring the technology into the future. And a few of those things really was to increase the bandwidth. That was because, as you've already seen, heterodyne systems that are currently being used tend to be very narrow band, and that's a limitation. And the other thing we really wanted to concentrate on was bringing the DC power that were down, because of course, if you're doing 1 or 2 pixels, that's fine if you're taking tens of watts or 100 watt. But as soon as you start talking about arrays, multi-pixel, you really need to bring this power down, and that's really true for, especially true for space instruments. And then the decadal survey that all of you know, we saw 4 talks, 4 excellent talks yesterday. A couple of them have heterodyne components to them. And then Martina wanted to mention that some people might not be aware of this. There's on the European side, there's calls out and will be for space instruments. And as far as I know, there is actually a proposal put in for a heterodyne instrument that's pending. And Martina organized this kind of a complimentary workshop earlier this year. So there's a lot of nice talks if you want to look that up. Okay, so I want to really do give a shout out to Sophia. I think that's actually, as far as the high spectral resolution stuff or instrument is concerned, is really producing a lot of nice results. And the German heterodyne receiver called GREAT, you can look at the noise temperature. It's really, it's not quantum limited, but it's about a few times quantum limited at 1.9 terahertz. And then essentially another advancement that was made is going from GREAT to upgrade. They went into a, something not needing liquid cryogens. It's a pulse tube cooler. And as you've seen, talks this from Sophia, there's some really nice results. This is the Gusto balloon that was a mission of opportunity. It was supposed to launch at the end of this year. I think now they're planning end of next year. So this one, it was less than a meter antenna, 0.85 meter antenna. It does have again 8 pixels for the 1.9 terahertz, 1.4 and 4.7. So it's already doing multi-pixel or will be doing multi-pixel astronomy. And this is currently a balloon that we are working on in my group at JPL. This is called Astros. So this actually pushes the boundary quite a bit. First of all, it goes to a 2.5 meter dish. And as I'll show you later, we're trying to actually do 2 bands and essentially combine them in one, but it does again do multi-pixel astronomy, and it does use again 4 Kelvin class cryocooler instead of using a liquid helium system. So this one will be able to do a number of science themes that are shown over here related to ISM. So in terms of now talking about the technology thrust, so one of the things that's really challenging for high spectral resolution system is the local oscillator, because you really have a very hard time getting a coherent source at these high frequencies. And this plot actually shows what we were able to do for Herschel. And this is really an apples to apple comparison. And this is what we got for Herschel at room temperature. Obviously, when we used it at 120 Kelvin. So this came up to about here. But in the years since we did Herschel, you can see now this is actually output power versus frequency. And if you're interested in like the C+ line at 1.9, we're getting close to 40 microwatts of output power. And then also the other thing to notice is that this is now more broadband than just being narrowband. And the other thing also is that we were able to actually bring the powers down quite a bit from the Herschel days, where the power amplifier technology has certainly come up. We're able to use GaN power amplifiers that have higher power added efficiencies, and then the efficiencies of the multipliers have also been improved. So this kind of puts state of the technology for local oscillators. It's already about a year old. But what you can see is 2 things I'd like you to notice from this plot. One is that now if you look at 2 terahertz, we can actually put almost a few hundred microwatts of output power. So that's really impressive. And what that means is now even with a single LO chain, you can actually, if you're able to take that beam and spread it with a Fourier gating or something like that, you can actually pump 64 pixels. And the other thing is, from the older data, you can see actually this falls, it almost falls like 1/f⁻⁴. But this new data where we've actually been able to use tricks with power combining, we've actually really stopped that degradation that happens with frequency. So this really bodes well for multi-pixel receivers. That really means that the local oscillators are not going to be the problem. And that if you go, as you can see from here, it's still falling quite fast. And so by about 3 terahertz, you're down to 1 or 2 microwatts, and that's probably not enough. So the other option for LOs for higher frequency, this is also an up-and-coming technology, is the quantum cascade lasers. So the push over there is recently we worked with UCLA to demonstrate these Maxell devices. And the advantage here is that you can actually control the beam quite well. And as the previous generation QCLs, the beam would be all over the place, and you won't even be able to couple it to the mixer. Now we can have a very well-behaved Gaussian beam. And the other thing we're trying to do is, by playing with the material technology, really have these working up to about 65 Kelvin. Right now, they usually need about 20 Kelvin or so. So this is again, it simplifies the system, it reduces your power requirements, it still gives you the local oscillator source that you want. So recently we did test one of these QCLs at 77, and the mixer was at 20 Kelvin. I'll talk a little bit about this. This is actually a newer material system, but we were actually able to get the receiver working. So here are some results from Europe. Europe's also been pushing the technology. So this plot on the left is from the Paris Observatory. This is a SIS mixer at the 500 to 600 band. This is the all-important band where the 5.8 micron water line is. And you can see it's very well behaved, and a mixer noise temperature of about 50 Kelvin. Just for context, at about I think 500, the quantum limit is about the factor of 2.5 from that. And also for HEV mixers that you need to go to once you go above a terahertz, this is again showing really nice performance of about 800 Kelvin double sideband for a 2.5 terahertz receiver. Okay, so this is something a little interesting. But before I talk about that, if you can just, sorry, this didn't come out quite right, but this is actually SIS mixer measured at JPL, and again in the 500, 600, and you can see this is also in the 60 Kelvin range. So again, and actually this shows you the quantum limit, so maybe a factor of 2 to 3 from the quantum limit. But this actually goes back to, if you remember the talk of Meredith yesterday about measuring the D2H. And you saw there's a big scatter on the D2H data that we have. First of all, we have only a handful of points. But another thing to note with that data is there's actually very large error bars. And some of those error bars are actually intrinsic to the mixer or the receiver itself, because you can have, for example, the H218 and H217 in different bands or different bands of your mixer, and then you have to do the sideband ratio, which is a pretty big problem. So this is something we actually proposed when it got funded, and the idea here is to actually have two LOs mixing on a single mixer, and by playing with the frequencies of the two LOs, as you can see over here, in the same passband, the same IF band, from 0 to 10 gigahertz or something like that, you can actually have the H217, H218, and the HDO lines in the same passband. And then you can actually really figure out your D2H ratio with much smaller error bars. So this, this we feel is really going to be very important, especially for the D2H measurement, but also any other measurements there you are actually trying to take a ratio of two lines. So we actually demonstrated this with the SIS last year, and earlier this year, the group from Purple Mountain Observatory actually demonstrated the same thing with the HEV receivers. So this is again something that would be very useful. So this also comes from Europe, from Astron and Delft. So this is, you saw a picture of this already. This is the Gusto HEV focal plane for the mixer array. And again, if you look at the results, which are tabulated here, I think the important thing to look at is perhaps this column, which it shows you that with these mixers now, we are within like a factor of 2 to 5 of the quantum limit. So we still have some work to do, but these mixers have been, receivers have been getting better over time. Okay, so this is another thing that's going on at JPL, which is to play with new material technology, and the idea is to have mixers that don't need maybe 4 Kelvin. And this is to look at this new material MGB2, which actually works fairly well up to even 20 Kelvin. And this shows you So this is still work in progress. So if you look at this plot on the right, you can see with the SIS at the lower frequencies, this is the result from the JPL result. We are actually below 2 times the quantum limit. And then the niobium nitride HEV technology is like right about here. And the MGB2 is this blue curve. So it's still not as good as even the niobium nitride. But there's no fundamental restriction to that. And we know that as we get better material and build better mixers, we can actually at least do what we've been doing with the niobium nitride technology. So similar kind of work is also being going in Europe. This is the group at Chalmers and Astronomate, and they measured a mixer at 5.3 terahertz. So what they measured was still about 2.5 times worse than the niobium nitride technology. So again, there is room for improvement here. So basically, I'm going through the different components of a heterodynamic receiver. So another thing we want to look at when we talk about bringing the power down is IF amplifiers. So again, there's been a lot of good work, and this is a plot showing indium phosphide technology, low noise amplifiers. This is from Sweden, low noise factory. And what you can see is, with 6 milliwatt of DC power, you can actually get 2 Kelvin noise temperature. But if you can take a slight hit on that, you can actually run this low noise amplifier with much less than a milliwatt of power. And the same thing has been shown with Joe Bardeen's group at Amherst. So he's been using a silicon germanium approach. And here again, we can get 5 Kelvin of noise temperature with actually about less than a milliwatt of DC power. So again, this is important to bring the total power numbers down for heterodynamic receivers. Another thing we needed to work on was the back-end processing. This is again, you remember, from the Herschel time, if you do use filter banks or FPGA technology, it can take hundreds of watts to do the back-end. And here we developed CMOS-based ASIC technology. And the first chip we did was at 1 gigahertz. The second chip was 3 gigahertz, which has been working very well. And there's a new chip that actually we just got the tape out, and it should go up to 6 gigahertz. And the thing to note is, obviously, this is ASIC. So this is essentially the technology that's in your iPhone. So the power and the size and the mass have all come down drastically from, for example, what we would have used a few years ago. And this is actually, so this is the board that we did for prototyping in the lab. It had a USB connection. And this is the same board done with flight compatible board parts at JPL. And this one looks a lot nicer, but it's also a lot more expensive. This is undergoing some testing. Okay, so then how do you make these multi-pixel receivers? So this is where this is a currently funded SAP, where we're actually stacking these. And so if you look closely, you'll see 16 diagonal horns. So this is actually a 16-pixel local oscillator array that we have tested in the lab. The other thing we want to do, as I mentioned early on, is the bandwidth. This is really critical. So if you look at what is the current state of the art that's flying on Great and Gusto. So these 3 bands, like the 1.4, 1.9, 4.7, you really have to do as different local oscillator system, different mixer systems. But we have actually made some major improvements here, and what we have done is by cleverly doing the RF design on the multipliers. What you see is this one chain now. I guess maybe the size of a Snicker bar. We can actually cover all of these lines. So the CO line, the N plus line, the CO13 line, then the C plus line, the HDO line, and even the OI line. So all these can now be covered with a very compact system. And to give you a sense of this, this is what we flew on SPO2. This is the 4 pixels for 1.4. This is the 4 pixels for 1.9. And they needed to be water cooled because it was so hot. And this has all been shrunk to something like this. So this is the 4 pixel thing that you can actually get 1.3 to 2.06. Okay, and then my final slide. So we are thinking beyond that. That's very good, but we're thinking, what if you really wanted to go to hundreds of pixels? And this is a JPL internally funded project. And I think the way to do that is to really use photolithography and also use this approach where you get rid of the beam splitter because you actually lose a lot of power there, and come up with a kind of a rather novel way of having an LO and the RF coming in from different sides. So this is a work in progress. Essentially, you use leaky wave antennas and lenses to really couple the RF and LO power, and you use silicon micro machining to provide waveguides for the mixers. And we were hoping that once we demonstrate this, we can really go to a very large pixel count. Okay, so I'll leave you with a quick summary. I think we can easily do, as I said, 100 pixel array. This is a high DRL technology, and obviously cooling is not required. And I think the future for this technology is really with multi-pixel instruments where the science throughput should drastically increase. Thank you for your attention.
Questions now?
Thank you for that excellent overview of the heterodyne system. I find your use of the second local oscillator to get another line interesting and intriguing also. Is there a synchronized penalty that you pay in doing this? I mean, as much as you bring another signal into your IF band, the second local oscillator also mixes some of your signal that was away from the band, right?
Yeah, so what we, I mean, if you have to do some careful planning of the LO frequency and the filters that you might use in the IF. So what we found is that you actually don't take a penalty, and that's really the useful thing.
Yeah. Other questions?
But this will not work for any receiver. This is actually work for SAS. There's a special case, of course, because of the SAS technology.
So one of the issues above 2 terahertz is the local oscillator cannot be frequency modified anymore. Can you say a few words about the tunability of cascade?
Right. Yeah, that's a good question. So with if you, I mean, historically, I think the big difference that we were able to do for Herschel was to have local oscillator electronically tuned, and that made a big difference. Now with the QCLs, traditionally they have been narrow band, but I think there's ways of tuning it. For example, I've seen people build up arrays, and so you go from one chip to another, and you can get tunability. You can also get some tunability with thermal tunability, but that unfortunately is a little slow. So what you really want is electronic tunability. Yeah. So that's still a little limited, but there's work that's ongoing.
So certainly this scaling up in this multi-pixel is really, it would be a huge step forward. And I'm just curious to understand what you think your time scale is that you could actually produce something.
Okay, well, that obviously needs a little bit more thinking, but I mean, if you want like a 64 pixel, there's really no technology development, a lot of the hardware is already demonstrated, but you still have to bring everything together and put it together. I don't know, maybe something like 18 months to 2 year kind of a time frame.
I have a quick question for you then. So some of these experiments are considered maybe both architecture. And for a system where you're injecting the local oscillator, like buying the astrophysical peak, say, like very long, it's slightly off by before. Maybe there's worry that because you're having to have a support coming from your more mellow, that you can't have very good spread of control. So are there alternatives to quasi-optically coupling the local oscillator, like the base guide, or is the local oscillator too large?
Well, that's a very good question, and as you probably know, the STG team kind of struggled with it, and eventually I think the solution was that, because the issue is that you want the local oscillators to be at room temperature, because they are the power-only components of the system. Now, the mixer itself doesn't take that much, power. There are some technologies, for example, you could think about dielectric waveguides, which tend to be lossy, but there is maybe a way of having, dielectric waveguides at a lower frequency, and then doing the high multiplication stage close to, at colder temperature. And so, instead of having a break at the high frequency, you have a thermal break at a low frequency. Yeah, but that's an issue that once you have both of these systems, that needs to be looked at.
Are there any final questions? Let's thank you. I think now is time for our large group discussion session. Yeah. Okay.
Well, getting tired. So why don't we do the thing where we have the 5 groups line up and go through it real quick, and then we'll open it up. We had a 2-3 slides about the things we have been hearing from multiple places, and sort of wanted to synthesize with you, and then we'll open it up and see what it is we want to come from this 3-day experience. Okay, so do we have representatives? Has everybody left? Group 3.
Any other groups?
Those are 5, right? Yep, okay. Come on up.
Okay.
We group 1.
Okay, we need group 2. Anybody from 2? Okay. Success. Yeah. Okay, hi, I'm Carrie Volpert. I'm representing group 1, I guess. I should just shout. Can you hear me? Ooh. Okay. We were a relatively small group, so would love to hear from other people in a way that's more representative of everybody. But our question was, in the limit that Sophia does end in 2023, how do we best position our community to keep doing the cool science we like to do? And how would that impact the community stability? And what specific science areas would stall? So one thing that we wanted to put as the first point was that, while Sophia is expensive, a lot of that money goes into funding the infrared community observers directly. especially early career observers, using, the funding that comes with observational data. So we did want to note that cutting loose SOFIA would dissolve that money back into NASA's general budget and away from infrared observers. And then we went through a couple specific science areas and highlighted them. One was extragalactic science. We noted that high redshift studies, to our knowledge, may not be very strongly impacted. However, the loss of SOFIA would impact our ability to do certain science observations of extragalactic galaxies in the nearby universe, which sort of allow access to a different scale that informs upon the higher redshift extragalactic science. So another point was solar system science. SOFIA is sometimes used to observe planets in our solar system, and in some cases, it's uniquely positioned to do so with certain lines. And so the loss of SOFIA would disable the ability to follow up on some of this initial promising science. And it would also mean a loss of a little bit of a connection to that part of the astronomy and planetary science community. So we thought that the science component would stall. Time domain astronomy. It was pointed out that SOFIA is currently the only instrument positioned to do time domain in the, I said in the infrared, but really in the far infrared. With no SOFIA, that would really limit the ability to do certain types of time domain infrared, and the science would stall. Velocity resolution. So SOFIA has this great ability to give you high spectral velocity resolution to recover dynamical information about individual infrared tracers and components. So this is work that would be really hard to replicate in a platform like a balloon. We think that this also could stall. And then we had two recommendations that we talked about generally as a group. One was to put an emphasis on how to best utilize the data that SOFIA has already produced by looking really hard at how to make a successful archival program that can still make use of the abundance of data. And the other recommendation was to systematically identify some really specific science questions that are left hanging if SOFIA is not able to follow them up, and to try to go back in and think about potential other avenues to pursue these science questions so they're not lost. Thanks.
Okay, I'm René Janssen, representing Group 2, and our question was, in the limit that SOFIA does not end in 2023, what scientific and technological impacts could it make for the probe mission, but also future flagships? We started our discussion basically thinking about timelines, and especially for hardware, it became clear that affecting a probe mission would become really difficult. Because the end of phase A, when more or less the design for the probe mission will be finished, doing new hardware on SOFIA is nearly impossible. However, potentially some software development could be done and tested. If we can look towards a more long-term scale, for example, for a flagship mission, we brainstormed a lot about what technologies demonstrators could be possible there. Unfortunately, we ran into a lot of what we thought dead ends, but the most promising to us clearly was the demonstration of a very large format heterodyne instrument, as Imran in the presentation before also pointed towards. We came a bit short on specific scientific impacts, but I think the main value which we saw is that a discontinuation of SOFIA, or at least the continuation of SOFIA until the probe got launched, would be the ideal opportunity to continue training astronomers and new generations so that they are ready, not only in person, but also with all the tools and to analyze any future data coming out of the probes or future flagships. And we thought yeah, the proven, like the, yeah, so for what we brainstormed is how do we, how can SOFIA, even for probe missions, show that this is extremely important, was by not convincing so much us, because we are probably all convinced that infrared is or far infrared is an important science, but help use SOFIA to show to other astronomers at other wavelength range that the far infrared can be a very valuable contribution to their science, and therefore make them more enthusiastic for our probe missions. Potential precursor science for probes or flagships would be we thought would be strongest in polarization science and finding local analogs for high Z astronomy. And that's it.
Hello, I'm Jessica. I'm with Sophia, Jessica Sutter. So maybe biased, but in the right direction, hopefully, for this question. So our question was, what are the scientific and technological justifications of Sophia operating into the next decade? How would it fit into the future landscape of IR experimentation? And I think a lot of what we discussed has kind of already been said by the previous two slides, but just to end earlier this morning by Margaret and Bernard. But just to say again, Sophia addresses half of the science priorities of Astro 2020. And really specifically, it provides these local analogs and context, local analogs to high redshift studies in context for current facilities. So I think the word synergy has also been thrown around a couple of times, but synergy between Sophia and then Keck, ALMA, and JWST. And if we don't have these local universe comparisons, it's going to be difficult to say how accurate our more high redshift diagnostics might be. Sophia is well suited to current demands for heterodyne high spectral resolution spectroscopy with the 2-meter aperture. And thus, see if I get this right, because the heterodyne doesn't depend on the cooling as much as the aperture size, Sophia is really well suited to do these sorts of tests. And then again, kind of on that same note, that technology maturation and really driving this heterodyne tech has already kind of resulted in the Hermes, which unfortunately didn't pan out, but it's in an advanced state, and there's already these kind of demonstrations for future probes. And Sophia is just this kind of unique testing ground where there's high complexity in between the communication between the detectors and the mirror and the observatory, but that maybe balloons can't necessarily replicate in exactly the same way. And then just, again, things that have kind of been said, that Sophia provides continuity for IR scientists, for IR science and the community, and keeps knowledge going in the infrared and draws in early career scientists, the early career researchers. And if Sophia is canceled, there could potentially be 2 PhD life cycles before a probe is launched, which would make it difficult to continue infrared astronomy. And also Sophia provides a platform for building new software and calibration strategies that could be developed before a probe launches, and that there are some legacy programs that are still in progress, and getting those finished would provide a really rich archive for infrared astronomy research.
Hi, everybody. I'm Angie. I'm a grad student here at CU Boulder, and I'm doing my PhD thesis work down the road at NIST. And I'm representing group 4. So our question was, what new suborbital capabilities would best enable the development to do new science and develop new technology? And we spent our time just sort of not really in an attempt to emphasize creativity. We weren't really constraining ourselves to things that we saw were immediately feasible, but things that we would really like to see. So some ideas that we had were, we spent a lot of time talking about the enhancement of ultra long, meaning 100-day duration balloons, for example, super pressure balloons. And this was motivated by the fact that in the US, there is a restriction for flying balloons where you cannot fly over overly populated areas. And I'm sure a few people in the room are familiar with the troubles with flying balloons in Antarctica, where you're restricted to both the Antarctic summer, and then the weather can just always be a really tough issue to mitigate. And we estimated $4 to $5 million a year would be wonderful to develop something like this. And the limitations we saw with this were mostly power consumption issues with cryogenics. We also talked about aerostats, meaning balloons that were, instead of flying, and you have to worry about flying over overpopulated areas or weather, they're just tethered to the ground. So you mitigate a lot of those issues that way. We also floated the idea of drones. We know that NASA has used drones for earth science applications. They would take some creativity to figure out how to actually put a telescope on a drone, but that was something we talked about. In the group, we expressed that ballooning is just hard. So one solution would be to continue with the same technology that we already have, but just like doubling our budget would be great. And we also thought about using sounding rockets for far infrared technology development. This has already been demonstrated with Cyber from Caltech. And this would get you 1 to 2 observations a year for about 10 minutes. And this would also be a really great way to just sort of raise the TRL of a lot of technologies that we're trying to develop. That's us.
Okay, so I'm John Groh from NIST, and in our group, we're supposed to talk about the role of balloons in a Sophia-less future. So, I mean, I think we've all been talking about how we love balloons for training people. You're not just in charge of that third knob from the left. And maybe not for detectors, but for other stuff, you can improve your technology readiness level. And at least for pointed science missions, I think they recognize you can do some, but not all things, but they're of course not, they can't match the cadence of a plane that just takes off whenever you want. So I think to get around some of the things like unpredictable flight times and low cadence and bad weather and infrastructure for supporting multiple cryogenic payloads from the South Pole, there's just a general recommendation to, not exactly sure how this would happen, but lobby the people who are in charge of the balloon program to increase the capability to have more of those. We also talked a little bit about adding some cultural acceptance of just being ready to lose your payload. Maybe instead of spending 10 years working on something that you really don't want to lose, maybe spend 3 years working on something that you kind of expect to. But on the balloon side, just for actual technology things, it was brought up that standardizing the platform might limit some people, but could relieve some engineering burden from the actual individual PI-led teams. You know, do we really need grad students designing gondolas? And we also talked about the Batman style way of catching payloads and other things, or floating them down more gently, and potentially just having workshops to discuss balloon things, where you get the instrumentalists and the balloon people in the same room. And then I think also we talked about the ultra long program where you start from New Zealand or something like that, as was mentioned before. And I guess we also mentioned to some extent having a general observer component for balloon missions, although I don't know if we reached a consensus on that. Just leave this up here.
Ironically, I'm not in the balloon group, but I do have a poster here for it that's very poorly printed. But you can still read it, which is what's important. So I've been thinking about this for a while, and I would love if we would as a community, come together and figure out how to increase the cadence of balloons. Unfortunately, that's a really hard problem. I really do like this idea of having like a generalized gondola, but that has its own challenges as well. And I think it would fundamentally change the way that we make instruments for balloons a little bit, so that may not be bad. But one of the general recommendations of the little poster is, you know, after this big call for all these science cases for probes, the community is going to be left with, you know, a survey of a ton of science cases that people are interested in and what their requirements are. And I think at that time, it's a really rich opportunity to go back in and, you know, collect science cases that balloons might be capable of doing, or not even just suborbital projects that the probes haven't taken up, and for us to revisit as a community how to really take advantage of balloons. The ultra long duration ones look really promising. They haven't flown yet though, so who knows? And they are looking at general observer programs for the long duration ones, but I don't think it's possible with some of these really short duration. So those are my comments on balloons.
Since we're talking about ballooning, what hasn't been discussed yet is whether we could tap into, is it called Worldview, One World, the commercial, taking people up to the stratosphere to kind of piggyback something on. I know you can't put, I know it's like, you can't put a big telescope, but it might provide an opportunity to get more access to the stratosphere for what other technical demonstration. I think it's called Worldview. Yeah.
Well, I think balloons are definitely the answer for how to get to OST. I mean, that's the real question. How does the community get from where we are today to OST, particularly in a scenario where the probe turns out to be an X-ray probe? And the Pioneer program can provide that answer. There's no programmatic development. There's no technology development required. These are 5-year projects. You're flight ready in 4. They're $20 million a pop. When Sophia goes away, NASA's saving $80 million a year. Pioneers are an annual solicitation. If they just took half that savings, $40 million, you can increase the number of you could double the number of pioneers that occur every single year. They're flight ready in 4, so you'll have a whole plethora of flights between now and OST. And there's nothing to develop. The technology is there. I mean, if the super pressure balloons advance, that's great, but you don't need them. You don't need them right now. You don't need a common platform. Okay, you can have a large number of balloon experiments that can do fantastic science and can field all of our foreign threat technologies to keep the community alive. And that will be a more effective thing for the SIG and the COPAD to advocate for. I think advocating for Sophia, to reverse the decadal decision on Sophia, I don't think that's going to be productive advocacy. But putting the Sophia operating funds into increasing the number of Pioneer missions that are selected every single year can do tremendously positive things for this community. And that's something I think we should think about.
So one thing that I did not appreciate about balloons before the discussion today was that they are not really good at providing general observer programs and involving the community. And so I'm a bit worried about the issue that people like me who are not interested in spending years in developing a balloon mission. Right? I want to go to an observatory rather than a proposal and get 5 hours of observing. And there are many people like me, and if there's no observational possibility for people like me, problem of being able to exploit infrared data.
Yeah, I think if I can answer that.
I think it just involves thinking a little bit differently than Sophia. Think about the KAO. In KAO, we never had any facility instruments. If you were simply an observer and you needed KAO data, you went to whatever instrument team had the appropriate instrument and say, you know, hey, I'd like to propose a flight with your instrument. And all those flights got done. In fact, the instrument teams were incentivized to say yes to you. And you know, with a fleet of Pioneer missions occurring every year, there'll be plenty of instruments available for you to reach out to. So you know, I think we can create an answer through Pioneers without developing anything.
Yeah, I don't know where to start. First of all, I think the reality of balloons as we have them at the moment is a different one. I wish we could actually, just by sheer increasing the sheer number of opportunities, we could create all these flight opportunities. And it has actually been proposed, but the reality is balloon missions have to wait for a long time for the right weather conditions. It is not like, okay, we just launch these things, right? So, and this is again my personal opinion, I think we are better off with creating an observatory solution that may be a little bit more costly than a normal balloon. Something I call it sloppy airship. So the characteristics of something like this is lighter than air, simply because there will be no airplane solution in the near-term future that can actually house such a big telescope. The 747 was the last one that we could actually use. So it will likely have to be something like an airship, but it needs propulsion, it needs the ability to fly for long times and then bring the hardware safely down and do general observer service observations. That is, I think, what in my mind at least is something that we should strive for. And until then, we should keep surveying.
So just to once more beat the drum of time domain astronomy, I think people are realizing more and more that time domain astronomy affects a lot more, you know, it's not some niche field, it affects all of those areas that we're interested in. AGM, planet formation, confirmation. And there's a huge gap. So, you know, and this doesn't mean just doing things with very high cadence. These are things where we have observations that are due to that. It's not a physical phenomenon, you know, evolve on its own time scales. And you know, when you start thinking what's available, it'll be JWST drops in 25 plus microns. You have some millimeter instruments on the ground. And wavelength between those. And if anything happens of great interest, and there are always things of great interest happening, we have no way of actually looking at that. And this is a matter where we have a lot of ability to look at time domain and other things. For example, LSSP and other instruments. And so I think it's a real problem to have this gap where we could put something on 15 micron, you can do it longer wavelengths, but they're just going to be it's a very useful gap. And so I think it's really important to plug this gap with some sort of
Yeah, sorry, I want to be clear again about balloons. Like looking historically at our ability to put up infrared balloons in the last decade, on average, we put up 1 or 2 a year, or in an exceptional year, 3. And that's, I'm not saying we put up 3 successful balloons, I'm saying 3 at some point take flight. So I'm not advocating it as a total replacement. And I do think some of these ideas are really interesting. I just wonder if they would, similar could as well. I think what we have right now is this ultra long duration program that hasn't gotten too much attention, but people have been working on it a while, and there are at least 2 proposed ultra long duration balloon flights in infrared. And if we could encourage the community to look at how they would like to utilize the general observer programs that have been suggested for some of those programs, that would be great. And if we could generally review some simple stuff that bottlenecks balloning, like our ability to land without like destroying the instrument. I think that would be beneficial to the community, and that's something that could be also reviewed on a sort of time scale event. And we can make changes on a sort of time scale event of probe already arriving.
A couple things. First of all, with regard to the point you just made, I don't think a high percentage of balloon payloads are destroyed on landing. I think it's about a low percent. What often gets destroyed is the outer skeleton, which is built to be destroyed. But the instrument itself, which is where you invested all the effort, is reused many times. Boomerang is just one of many examples. So I don't count that as a negative. It happens at times, but it's not 100% by any means. With regard to Sophia and balloon, if I could snap my fingers, I would extend Sophia into the indefinite future. But it should be remembered that a lot of the balloon missions that were mentioned today from Antarctica are, on the order of 20-day missions. And that's 20 days of 24 hours a day of observing. So 20 days of a single balloon flight is the equivalent of 60 Sophia flights. If you have 2 balloon payloads in the season, you have equal or exceeded everything you can do on Sophia hour-wise. So, we have to recalibrate our thinking, have a platform that works 24 hours a day, sort of like a space mission. And for 20 days, you can do a lot. So it's just a question of having a variety of capabilities so that the general observer can pick one or another to attack their problem. But it's not a case of 365 days of observing with one platform and a week with another. It's a lot more equal than you think.
I'd like to extend what Carrie said, but in a somewhat different direction. You saw yesterday, every one of the road proposals showed the plot, what's possible in that. There's what can be done with a cold telescope in space. And the factors, mapping speed or sensitivity, are orders of magnitude. Take everything that could be done, have a balloon flight every day, fly Sophia continuously, and do that for 1 million years. And you don't come up with what the cold telescope in space can do. So all these other things put together don't come close to that cold telescope in space. That's why seizing that opportunity is the opportunity of, so far, far-infrared astronomy in its entire history. That's the thing we have to focus on. That's the thing we, as a community, whatever kind of support we can give to that and to make it happen, that's how we get the most science. I'm not saying that other aspects aren't important, but if you think just science, and you think what mapping speed differences of, I think we heard a factor of 1 billion. Okay, for the big telescope, knock it down by a couple.
Yeah, but the problem with that is you putting all your eggs into one basket. I don't think that's a wise strategy for forward.
Right now, that's a real basket. The real
Just to be
potential
clear, I
basket.
was addressing the question of what are some of the means by which we can bridge the gap until the probe. So I'm not suggesting this is an alternative to the probe by any means. I'm a huge supporter of the probe, but what do we do in the meantime?
I understand, I'm just saying that there's a limited amount of money. And certain things are possible, but certain things aren't. Just, I'm trying to order things in terms of where they sit, and there's such a huge discontinuity with the cold telescope in space. The infrared community has been working towards cold, bigger telescopes in space for decades. And we're right on the verge of a major.
Yeah, no, I want to agree with you on that, Charles. That is something we should definitely be going for, but I do want to caution us not to accept the box that people put us in, that we only get one opportunity and we have to pick one star things and prioritize and only get to pick one. I think all these capabilities we're talking about are important. They will probe different types of science. It's true that the whole probe in space will be remarkable in what it's going to discover. But it's going to be probably focused a lot more on the finer things, because brighter things can be done with SOFIA or balloons or other opportunities. And maybe that's the way it should be done. I mean, if you look at the optical telescope system, they have all sorts of size telescopes doing things. But maybe this field needs a variety of sizes to address the different types of science. It doesn't have to be just one thing. And we can decide how we want to do this, but I don't think we should accept the box that you just get one. That's it. I mean, X-rays don't do that. We shouldn't accept that box.
I could follow up. I agree with that. I wasn't trying to be one-dimensional about this, but I'll mention that another thing that's in ASTRO 2020 is flagship, an infrared flagship, an even bigger thing. And work on that will start in this decade. And that's something else that we need to support. And that's in the, well, not, it's hard to predict how far in the future that is, but that's a real possibility. Why is it there? Why are these things there? It's because the scientific potential of the infrared and the scientific potential of the infrared in combination with other wavelengths, the panchromatic science aspects that need the infrared as one of the components are just so compelling that we recognize. And so that's why the report reads like it does. And the only thing really that trumps that is life elsewhere in the universe. And that really is what determines the order.
Charles, I think we're all in agreement that, we want the probe. And you can see the community is going after that probe opportunity with Boulder team. I mean, there's 4 candidate proposals. The X-ray folks, our colleagues over there, they also have 4 proposals. So, everyone's going after that opportunity with Boulder and their team. Maybe we'll win, maybe we won't. But we have to consider both possibilities. OST is the end goal, and it's in their SAM diagram. So, it's in their planning. And the goal map is going to, as you say, it's going to start for OST. Will start soon if they're good proposals. And there has to be some place to field those technology products. And this Pioneer program can give us the answer to that with zero development of anything. Developing an airship and so forth, that takes time. And by the time you get that flying, we might have won the probe, or we'll be close to OST. Pioneers, you're taking something that headquarters created, and you're saying to headquarters, hey, this is a fantastic solution, temporary solution to the problem that we find ourselves in as a community. And it can help us get to the decadal goal of OST with no development. I think it's a no-brainer.
You make a very good point. I agree completely. And we should be taking full advantage of that. Absolutely. And the possibility of that program with balloons and space things, that's a way of trading off the balloons and space and the time. And what can you do? So yeah, I agree completely with you. It's an excellent point.
We have time for a few more.
I do think one thing that would be useful, I'm not sure it's Meredith and I will carry this ball forward, but we do talk to other people in the room do too, right? We're all pushing in the same direction. But to the extent that there's concrete feedback about what our priorities are, that would be useful to know.
It's sort of a question of the balloon community, but what are the issues with the PNR emissions? You always see a very small fraction of the sky at all, and that makes it hard to actually find synergy with other observatories and such. And so, given all the different sites where people watch balloons and such, how much of the sky can we cover, and what are the constraints of sort of targeting and such?
Tom, you do as well as any Southern Hemisphere ground-based telescope in terms of coverage, if not better, because they're at 14,000 feet or so, and the balloon is up at 120,000 feet. So you cover the Southern Hemisphere pretty comprehensively. Now, of course, the bigger limitation is time of year. You always launch these balloons sort of in the Antarctic summer, which is December and January. So, whether a source is available or not during that period is a question. You don't have a lot of flexibility with sun avoidance. If something's close to the sun, it's not observable. But you still get a pretty good sample of the sky. I mean, as good as any southern ground-based observatory in general. So that's not a main limitation. The problem you identified is real, that you don't have right now a good analog in the northern. You get 5 to 7 day flights from Sweden to Greenland, but you can't do sort of 20-day flights. You can do a ride from Antarctica. You can sort of overlap a bit with what can be done from Hawaii. Not too bad.
I'm just curious to know if balloons have a limitation on what any kind of rain they can cover. So limit on how long it goes, how wide it goes.
Well, you can go to the zero elevation. It really depends on your cryogenic system. If it's properly designed, you can go to zero. The upper limitation is usually about 65 degrees because then you begin to view the balloon. But, not horrible. 0 to 65 is pretty good.
Any other questions, responses? Okay, then perhaps we'll move towards our wrap up.
I'm doing the wrap up. So it's not just my opinion, it's like more than just me.
Okay.
Okay, great. So over lunch, I made some slides of things that we've heard as IR STIG leadership members over the course of these last 3 days that stuck out and seem to be kind of repeated themes. So we're going to go through them. And then, I don't know, we can just take that as wrap up. We can open up for additional thoughts from anybody. But yeah.
Yeah, I guess going back to my thing, I was just meandering what you were saying. That was sequence there. what's the goal? I guess the goal here is to come up with at least a concrete set of bullet points we can all agree on, more or less. And that will action IRSTIG, and I suppose by proxy, OPAC, or whomever, to do certain things and advocate for certain things to people that try to listen to us. Now, you know, affecting changes may or may not happen, who knows, but they, you know, NASA claims to listen. So we should think about what we want to say at this.
All right, so this was, so I have like 3 slides of suggestions in different categories, and this is sort of a general point that has come up a couple times and we felt was worth making, right? The idea that the IR, infrared wavelengths, is really 3 different wavelength regimes, right? The near, the mid, and the far are quite distinct from each other. And what often happens is that those, you know, well, they also have 3 completely different enabling technologies, right? It's not the same thing to build the mid-IR telescope as the far IR telescope. And what happens often is that they get lumped together into this the IR, and that's really a misrepresentation, and it's problematic when we advocate for our community. I know we didn't have a concrete way of fixing that, except to state it as a reality. And then, you know, one caveat on that is, can we use this to our advantage in the coming years? Because so long as we are going to get lumped into the IR general community, IRSTIG is going to be, you know, showing off IR science to the broader astronomical and public, you know, so can we use that to our advantage so long as we are going to be grouped together?
Well, there's the corollary, which is the community saying, why do you need more telescopes? So we have IRSTIG, right? So they're going to say, why do you need it?
Right.
And the answer is, well, because they're different. But the perception out there may not be that, right?
Different, but still different.
Yes, different, of course, yeah.
Okay. Okay, so the first category of recommendations we put together was advocacy to NASA, right? So our higher ups. And the first thing is, I don't know, maybe more of an acknowledgement again that says that the fact that we have this range of probe concepts currently under development is really kind of a natural consequence of how they've structured this probe call, right? It has a strict cost cap on it, which is lower than the decadal had even said. Because of that, people are wanting to use their different technological capabilities to explore very different regions of the sort of parameter space we could look to do science in, right? Comparing high spatial resolution to high spectral resolution to survey modes. Those are all valid directions to go in science-wise, because we're putting it in $1 billion box. We can't do all of it. So this is sort of a natural outcome of how they've done this. Okay. The second thing is that if the opportunities from SOFIA are removed, then we desperately need to increase opportunities for IR science and technology development someplace else, right? Maybe that's balloons, maybe that's small sats, maybe that's pioneers, maybe it's explorers. And we'll note then that even if we get a IR probe, which I sure hope we do, that won't launch until the 2030s. So that, you know, SOFIA ends in 2023. This thing launches in 2033, we still have a decade, even if we get the probe. So somehow we need to bridge that decade from a science perspective, at least.
Yeah, so I you know, part of point 2, I think might be to think a little disruptively about the paradigms. So, for example, the balloon things you guys have been talking about have been historically true, but you know, building on what Matthew's saying about pioneers and whatnot, why don't we start treating balloons like McDonald's hamburgers, where we are okay losing them, and we can go on ultra long duration balloon flights, and we can not be restricted by Antarctica summers and whatnot, because these are very restrictive requirements. And if we can get more creative and advocate to NASA, then what we really need is more capability. That might be constructive. That might go somewhere on a short time scale, 5 years, right? And it would not conflict with anything else that may be happening with the probes.
This leads back to obviously to Margaret's point, where she said all that, just like, you don't have to be in a box where we only have one thing. Like we can want all of the things. That's an okay thing to advocate for.
I just want to comment
Number two is advocacy. Number one is a comment. It's not advocacy, right? You're not.
Okay, we wrote one more as like, this is feedback to NASA. They gave us this problem in the box that we're currently trying to fit in. So it's not, I mean, I'm not going to change the protocol, I don't think. So therefore, it's more an observation back to headquarters of what they, a comment to NASA.
And a comment to us, because we went into this thinking, oh, well, maybe we need to consolidate. Maybe the right thing to do is desperately cram everybody into the same box and be happy together. I think it seems like people are accepting that perhaps that's not necessary. Perhaps it is helpful to have more people. I don't know.
I'm a little troubled by number one in the following sense. If we frame it as a complaint that we were only given $1 billion, I think that that'll fall flat or worse. Since prior to this opportunity, if you didn't get a flagship, the most you could do was a bid. So this is a big step up. And even if it doesn't meet everything in the decadal, the fact that they've removed geo programs from this cost cap is big. So I think we'll come off as whiners if we say, you know, we were really constrained at $1 billion. And you know, I would say that first sentence or the first half of that first sentence is true of every mission, not just $1 billion class mission. No matter what your cap is, you find that your head is brushing up against the ceiling. Well, we weren't a confirmed mission. So, you know, we didn't have a ceiling, we had a cloud that we could stick our head into. But look at Roma, you know, once you have a cost cap, you have to work to. You're always, you know, wishing you had more capability. So it's not just the case for our approach.
Yeah, just to say it out loud, I don't want to say this is what we would say to anybody in public. So it's a valid.
No, and in writing that, it was more of a like, this is something that we should all note and headquarters should know because the choices they make in these things dictate the playing field and coming out of that, not like in a whining way. Love $1 billion to build a space program, that'd be great, but you know.
Yeah, I definitely agree that we would want to rephrase this in a positive way and be very grateful for, you know, what we are being given. But I think it does go back to the first slide again, where we are a very large community over a very large parameter space, and we are being asked to kind of fit in this box. And like, this is a little bit more constraining than say maybe the X-ray, maybe I'm just characterizing how broad X-ray parameter space is, but like, we are being asked to do something a little bit difficult. And so I like this comment, spun in a positive way, just to make sure that they understand that we can't really address everything in the decadal. You know, we can't address everything that we would ever want to do with this. And we're hopefully okay with that. But it is a constraint that everyone needs to be aware of, so they can't then later be like, well, the far IR probe doesn't do everything the decadal wanted us to do. And so we should go with the X-ray probe or something like that.
There's a bit of a misunderstanding here about what the decadal recommendation was and what NASA did. The decadal recommended $1.5 billion in the program, and that's exactly what NASA did. $1.5 billion to NASA is $1 billion to the PI. That's just the fact. So NASA implemented exactly what was recommended. The launch, the GEO program, and the reserves. They're NASA, and they have them. So 1.5 equals 1. That's just a fact.
Next slide. Well, maybe less contentious. Then we had community engagement, which, you know, first point was that we really need to make a concerted effort as an IR community to reach out to the broader astronomical community. This includes especially early career researchers and scientists with the note that actually getting early career researchers into this field requires data and funding and technology development opportunities. And also reach out to the public, right? We need to convince people why IR is exciting, and we need to think about how IR observations complement other observatories, multi-messenger synergies, time domain type science. That's words of thought. Second was that we should engage theorists and encourage more IR simulation type work. And then to kind of leverage that last, point from the first thing here, that we should partner with and leverage other observatories like ALMA, thanks, George, to engage the scientific community, right? Because we can do a lot more of that than we already are doing, and I think that would be to our advantage.
Along these lines, I think we can reach out to the community. We have the PR material already, and that's the origins concept study. I think we can pat ourselves on the back that the probe recommendation was explicit in mentioning the FAR IR. And it didn't have to. And this was without, I'm told, I haven't looked over the steering committee, without a single far infrared astrophysicist on the steering committee. So I think we made a damn good case to people who were not predisposed to favor us. And the concept study, I think, will remain relevant for quite some time. And I think it's a well-told story with beautiful graphics. So I don't think we have to entirely reinvent the wheel here. It is something of a guidepost for us, how to reach out to people who are not intrinsically infrared astronomers, but can come to realize that our science actually does better.
So we have your permission to steal anything we want.
Okay, with respect to reaching out to other communities, as much as we want people in other domains to pay attention to infrared, the infrared should also start doing things in other domains. I will bring again AGBL as an example, because it's design and development phase, just starting there, and all of us should contribute to it and figure out what is it that you want from there that will add to what the infrared community wants to do.
To speak more to community engagement, so I was part of group 5, and one of the recommendations that we had was to have a workshop on balloons. So a lot of the people in that particular group, including myself, we have some familiarity with balloons, but not really, probably not sufficient to be talking more about it. And we were really interested with what we found out, things that we didn't realize were being done before, such as development that had to happen with the gondola to even get these things launched. Things like ultra long flight duration balloons. So I think as part of this community engagement, having a workshop or multiple workshops on balloons where we invite different communities would be really valuable.
So I will say, message received. I personally am serving on the organizing committee for Sounding Rocket Workshop this summer because we want to reach out. That committee is a little bit different than the one in the room probably, but I can certainly pass on to the balloon office that there's this desire and they should be doing stuff because it's a good one.
Okay.
Yeah, I just wanted to point out here, so when it comes to engage theorists and other communities that have a vested interest, and I'm thinking here also, for instance, about the laboratory groups who simulate ISM rates and whatnot, right? What I'm missing at the moment, I haven't heard for a long time this request of doing more lab work in support of in particular heterodyne astronomy and the like. This was the big shout out after special flu, because we saw all these amazing forests of lines and hi-fi, of which we could interpret something like 20 or 30%. And we had no idea what the rest was, but what we knew was it was all real. So I don't know what happened to this. Don't we need something, some more effort in that respect?
Were you gonna answer that? Sorry, I'll answer real quick. The NASA group is maybe no better than I do, but I am told that APRA is increasingly concentrating on laboratory astrophysics for the reasons that you mentioned. So in fact, the funding profile for laboratory astrophysics has been on this. Maybe it's not very large yet, but it's up.
Just really quickly, one thing I did mention earlier, the fact that some people are, but maybe not everyone, is it all the 2030 vision. So we're trying to double the bandwidth of the receivers, increase the capability of the system, better spectral resolution. And the reason I mention that is that that's on the same time scale as the program, right? So we're in the early phases of this, and this is something that you all talk to us about, think about how you provide this together. And Jessica mentioned the far IRs can provide a lot of low redshift things that you put high redshift on. There's a lot of really complementary stuff there. And it's the right time scale for the prohibitions. It's something.
I haven't really had the time to think about that because I just ignored that activity so far. But there is the proposal science workshop at the end of the month. And I think if that's for our flagship missions, concerning technology and as I understand also preparatory observations. So that might be another go-to point for essentially everybody in this community who was participating in this conference to advocate for infrared and potentially to learn how to make use of the opportunities that we are provided by the Professor Science framework.
Is anybody planning on going to that? Okay.
We should make sure people are going to that from our community, right? That's an important opportunity for us to engage with multi-wavelength perspective. Okay. On that, I don't think you can mention. My impression is that one of the most publicly visible and like PR relations projects in infrared right now is Sophia. So if, we're looking at a future that doesn't have Sophia, I think we should seriously consider actively continuing public visibility and engagement, especially with like students and educators through other projects.
I just wanted to make a comment about the laboratory astrophysics. That's true that APRA is increasing the funding and the opportunities for laboratory astrophysics. But what the laboratory astrophysics community needs is also knowledge of what you need. So I would add to that bullet about peers to engage the laboratory astrophysics community to encourage more infrared laboratory astrophysics work to support your science.
Okay, let's move to our next slide because it's pros. Leave us time for comments on this, so we can actually end at 4. So there's 2 points here. One is that these prohibition concepts that we're currently studying carry a huge amount of responsibility for our IR community, right? These mission concepts need to clearly demonstrate that FAR-IR is the best direction to push right now. I think this is an obvious statement, but bears repeating, right? The FAR-IR is a unique space in which we can make, at least 100 times improvement right now in sensitivity and science discovery space, and that's not true in other wavelengths. So we need to make that case, and we need to make it well. And the next one here is that we need broad community input and involvement throughout the entire probe concept development process. And I think that this would make it easier for all of us to come together in the end of this whole process, no matter what concept is ultimately chosen. Maybe those are not controversial points. Excellent. Okay, what do we have next?
Oh, next slide.
Yeah, sorry. Oh, let me put this on here, that perhaps we should think about having another workshop like this some point in a year or two, once there is a probe concept that has been selected, that maybe the IR STIG can continue playing this role where we bring the community together and try to chart a path forward once we have a concept that we are hopefully rallying behind to push to the next phase. I don't know if Mike and I are going to organize that, but.
And of course, we should not forget that hopefully the pandemic being recession at the moment, we have the IRS workshop that we always have. So all of those people in the room here should show up at those IRS meetings.
Yeah, whether rightly or wrongly, COPAC wanted to do a joint COPAC thing and cancel the individual citizen states this summer, but yeah, I would imagine we'll have one on people.
Okay, I think that's it. Next slide. So thanks everybody for coming and staying for 3 days and engaging with us. There's a lovely photo from the mountains. Very anticlimactic now. Confetti to fall from the ceiling.
I was going to say, figure out what you're talking about. Yeah, we'll take it. Yeah, right.
Do they really care about the community?
Yeah.
I don't know.
Give this to you, you can hand them out to students or. Okay. Well, we need that too. Yeah. Yes.